Hello there and welcome to Science for Sleep, a place where late-night curiosity settles gently beside the quieter corners of the cosmos. If you've been looking for a calm drift into wonder after a long day, you're exactly where you need to be. Tonight, we're heading far beyond our familiar skies, beyond the soft glow of nearby stars, beyond anything that could ever fit into an ordinary map of the universe. We're heading towards something enormous, something so vast that even astronomers whisper about it with a mixture of amazement and caution. It's called the Shapley Supercluster, and it's one of the most massive structures ever discovered. Not just in our region, not just in our galactic neighbourhood, in the entire observable universe. Before we venture out there though, before we stretch our thoughts across these incredible distances, I'd love to know where you're listening from tonight. Maybe you're wrapped in blankets in a quiet room. Maybe you're in the middle of a late shift trying to unwind with something steady and gentle. Maybe you're halfway across the world watching the clock drift toward morning. Whatever the case, and wherever you are, thank you for letting this small corner of calm keep you company. And if you find this journey soothing, or if you enjoy wandering through the deeper parts of space while your mind softens into rest, it would mean a lot if you gave the video a like or subscribed. It helps this sleepy little project reach others who might need the same quiet break you do. No pressure, of course, just an invitation if it feels right. Now, let's ease our way into the story. There's no need to rush. The Shapley Supercluster isn't going anywhere quickly. It's been out there for hundreds of millions of years, gathering galaxies like distant lanterns and forming a gravitational presence so large that even our own Milky Way is being tugged by its enormous pull. But we'll get to that soon enough. For now, imagine settling back a bit more comfortably, letting your breath slow just slightly and allowing your thoughts to stretch out far beyond the edge of what we normally see. We're beginning at a simple place, not with the supercluster itself, but with you, me, and the quiet sense of scale that comes from realizing how far this story reaches. One of the gentle things about discussing something as big as the Shapley Supercluster is that it gives the mind a reason to let go of the small stuff. Not to dismiss it, but to set it aside for a moment. When you think about something that contains thousands of galaxies, and each of those galaxies contains billions or trillions of stars, the frustrations of the day, the deadlines, the small urgencies, they don't vanish, but they soften around the edges. They become just a little easier to step away from. And that is part of the comfort of cosmology. Everything is so enormous out there that you can breathe out and feel a little lighter simply by remembering your place in it. As we move through this story, we'll be taking a slow path. Nothing abrupt, nothing urgent, just a steady walk through what we know about the Shapley Supercluster and why scientists became so intrigued by it. It's not the first big structure anyone ever found, but the more astronomers looked at it, the more they realized that it wasn't just big. It was extraordinary. It was massive in a way that didn't fit neatly into earlier expectations. It became an object of fascination because it seemed to sit in a category of its own. Something so heavy, so dense with galaxies, and so gravitationally influential that it might help explain why our own galaxy is moving through space in a particular direction. But before the details unfold, there's something grounding in remembering that even the largest structures in the cosmos are made of familiar building blocks. Stars, dust, gas, dark matter, all the usual ingredients, just a lot more of them, arranged in patterns so large that only modern telescopes and careful measurements made them visible. When astronomers first encountered hints of the Shapley region, it wasn't through a single discovery or a dramatic moment. It was more like noticing a pattern in a puzzle that didn't quite fit the expected layout. A gentle surprise, a quiet question forming, a feeling that something in that part of the sky was heavier than it should have been. Even now, if you could travel there, and you can't, not with any technology we have, you wouldn't see anything unusual with the naked eye. You'd probably look out at the same familiar darkness dotted with faint smudges of distant galaxies. The dramatic scale of the Shapley Supercluster doesn't come from how it appears to the eye. It comes from what we understand about its mass and its reach. Its influence stretches across hundreds of millions of light years, shaping the motions of galaxies that have never seen its stars directly. That's one of the quiet wonders of space. Things don't have to be bright to be powerful. They don't have to be visually overwhelming to reshape the movement of entire galaxies. Gravity does the work silently, patiently, without any need to announce itself, and in the case of the Shapley Supercluster, that force accumulates from so many galaxies and so much matter that the result becomes one of the strongest gravitational concentrations in the nearby universe. But I'm getting ahead of the moment. There's still plenty of calm ground to cover before we dive into how it all works. Right now, we're still easing into the scene, still getting comfortable with the idea that somewhere out there, far beyond the Milky Way, far beyond the local group, far beyond the Virgo supercluster even, there's a place where galaxies gather in extraordinary numbers, a place discovered slowly, piece by piece, only becoming clear after astronomers stitch together many observations from different eras. Picture this: astronomers in early decades scanning the sky with photographic plates, noting the shapes and positions of galaxies, trying to understand how they were distributed. They weren't yet looking for something specific. They were cataloguing, observing, measuring. But those measurements built the first faint map of the universe beyond our immediate surroundings. Over time, the structure of the cosmos started to reveal itself, not through sudden leaps, but through careful accumulation. The more data that arrived, the more obvious it became that galaxies weren't scattered randomly. They formed patterns. They gathered in clusters and superclusters. They stretched across the universe in filaments, connected like strands. They left enormous empty spaces in between, called voids. And among all those patterns, a dense region began to stand out. Something heavier, something busier, something that didn't behave like the rest. It would take decades before it was officially recognized and named, but the Shapley Supercluster was quietly sitting there the whole time waiting for us to notice. Even describing its distance requires a moment to settle your thoughts. It isn't a quick trip. It isn't even a distant neighborhood. It's about 650 million light-years away. That means when we study it, we're looking at light that began its journey long before humans existed, long before Earth had familiar life, even before many of the continents took their modern shapes. Everything we see from it is ancient by the time it reaches us, yet its gravity affects our galaxy right now. That quiet fact is one of the grounding parts of this story. The present and the ancient coexist in the universe in ways we don't usually think about. Light carries the past. Gravity acts in the present. When we look at the Shapley Supercluster, we're seeing what it looked like hundreds of millions of years ago. But when our galaxy drifts ever so slightly in its direction, that motion is influenced by what the supercluster is like right now, not what it was back then. A strange combination. But the universe is full of gentle contradictions like that. As we move through the details, the scale might feel overwhelming, but it doesn't need to. All of this is just a way of describing patterns in space. You don't have to visualize every galaxy, or every filament, or every cluster. You don't have to imagine every number. The important part is simply the understanding that this structure is massive on a level that makes even other superclusters seem modest by comparison. It's one of the reasons astronomers study it with such interest. The Shapley Supercluster sits near the limits of what we expect huge structures to look like. It tests our understanding of how the universe arranged itself over billions of years. But for now, we're still in the gentle beginning of the journey, still letting the idea take shape slowly, without pressure. The universe is vast, and this structure is a piece of that vastness, one that will gradually become clearer as we continue. When we try to understand something as enormous as the Shapley Supercluster, it helps to begin close to home, not because our corner of the universe is particularly special, but because it's familiar enough to give us a sense of direction. If we jumped straight out to the farthest regions, the distances would lose their meaning and the scale would feel unanchored. Instead, we start with what surrounds us, the cosmic neighbourhood we live in every day without ever noticing it. This quiet familiarity helps us take steady steps outward, one region at a time, without rushing. The place we call home, at least on the largest scales we can comfortably picture, begins with our galaxy. The Milky Way is where our star belongs, and where our solar system orbits quietly among hundreds of billions of other stars. It stretches about 100,000 light-years across, which sounds impossibly large from a human point of view, but in cosmic terms it's modest. Most galaxies of its type fall roughly in the same range. Even so, it's a good place to begin. Every night sky you've ever seen is shaped by our position within this rotating disk of stars. We're tucked several tens of thousands of light-years from the centre, not near the edge, but not anywhere near the core either. It's a stable, calm region to exist in, away from the more turbulent central areas where stars can crowd together more tightly. But as large as the Milky Way is, it's only one member of a small family. The galaxies closest to us form a group called, fittingly enough, the local group. There's nothing flashy about the name, but it describes the arrangement well. We share this region with a few dozen galaxies, though only a handful of them are large. The two biggest are the Milky Way and the Andromeda Galaxy, and they're gradually drifting toward each other. Not quickly, not even remotely. It will take billions of years before they merge. But even in that slow approach, you can sense that galaxies are not still objects. They're always moving, interacting, responding to gravity in calm but steady motions. Alongside us and Andromeda are several smaller galaxies, many of them faint, some of them difficult to see without precise instruments. They orbit around the larger ones like small companions, shaped by gravitational interactions over billions of years. The local group spans a few million light-years across. On that scale, the Milky Way is just one of many points within a much larger area, each galaxy gliding along paths shaped by long-term gravitational pulls. It's peaceful in a way, not because nothing is happening, but because everything moves on timescales so slow and steady that it would take millions of lifetimes to notice any substantial change. The local group doesn't sit alone in a sea of emptiness. It's part of a much larger arrangement called the local sheet, a flat structure where nearby galaxies tend to align in a shared plane. These sheets form because gravity and the expansion of the universe shape matter into patterns that aren't random. They stretch in long, wide configurations rather than clumping in every direction. Our local sheet gives us a sense of belonging to something slightly larger than the local group, a bit like realizing that your neighborhood is part of a wider town. You didn't notice the rest of the town at first, but once you do, you understand that it holds the shape of the place you live in. But even the local sheet is just a small part of something far more expansive. As we move up a scale, we reach the Laniakea Supercluster, a region that contains not just our local group but many others. Laniakea is about 520 million light-years across. That is an enormous distance, so large that it's difficult to attach any intuitive feeling to it, but it's meaningful to know that this is the structure containing everything within our immediate cosmic environment. Laniakea isn't a compact object like a galaxy. It's more like a web of clusters, filaments, and groups, loosely held together by gravity on one side, but also influenced by the expansion of space on the other. Within it are tens of thousands of galaxies spread across thousands of clusters, and its boundaries aren't as sharp as those of a galaxy. They're shaped more by motion than by a clear physical edge. When researchers identified Laniakea, they didn't find it by spotting a bright outline or a distinctive shape. They found it by mapping the flows of galaxies, measuring how they move relative to one another, and noticing that many of them seem to be drifting toward the same broad region. The Milky Way, Andromeda, and countless other galaxies appeared to be drawn along similar paths. These paths helped to reveal the extent of the supercluster, showing which galaxies moved together and which ones drifted away toward other gravitational centers. It's within this movement that something interesting begins to appear. Galaxies in Laniakea aren't just drifting randomly. They're being influenced by two major gravitational pulls. One of these is the Great Attractor, a region of space with a concentration of mass large enough to tug nearby galaxies toward it. This idea puzzled astronomers for decades. They knew that the local group and many neighbouring galaxies were moving in a specific direction, faster than expected from local gravitational effects alone. Something was pulling us, something massive enough to affect not just a small area, but an entire region of the cosmic landscape. The more astronomers looked at the Great Attractor, the more they realised that it wasn't a single object, like a massive black hole or an enormous cluster. Instead, it appeared to be the combined gravitational influence of an extended region, full of galaxy clusters and dense matter. But even this didn't fully explain everything. As observations improved, it became clear that the Great Attractor was not the final destination of these flows. Beyond it, farther away, there was something even larger exerting influence on our region. This is where the Shapley Supercluster begins to come into focus. The motions of galaxies in Laniakea suggested that the Great Attractor was merely one station along a longer path. The real centre of gravity pulling many of those flows lay beyond it, deeper into space, in the direction of the Shapley concentration. The Shapley region isn't close in any meaningful sense. It's hundreds of millions of light-years away. Yet the gravity from its enormous mass extends across those distances, contributing to the motion of galaxies throughout our supercluster, including the Milky Way. But before reaching Shapley itself, it helps to sit with this idea for a moment. The place we call home is not static. It's part of a larger flow. Think of it not as a river with water slipping through, but as a gentle drift of entire galaxies moving together toward a distant region shaped by gravity. This isn't a fast motion. If you measured how far the Milky Way travels in a year under this influence, it wouldn't feel impressive by everyday standards. But over millions of years, the effect becomes meaningful. These subtle pulls shape the long-term positions of galaxies and help define the large-scale patterns of the universe. When we think about our position within the cosmos, it's easy to imagine that everything is sitting still, like points stuck on paper. In reality, everything is moving through space, and these motions trace out the deeper structure around us. The Milky Way orbits its own centre. The local group's galaxies drift within their shared environment. The local sheet sits in a broader context shaped by the gravitational landscape of Laniakea, and Laniakea itself stretches toward other regions, forming part of the larger cosmic web. That web is the next layer of understanding. On the larger scales, the universe isn't a random scatter of galaxies. It's arranged in long filaments, broad walls, and clusters joined together in patterns that look almost like interconnected strands. These strands span hundreds of millions of light-years. Between them are vast empty volumes, places with few galaxies at all. When you look at a map of this cosmic web, you see something that resembles a complex structure rather than a uniform distribution. This pattern emerged because matter in the early universe gathered along slightly denser regions, forming threads and nodes that grew over billions of years. We live in one of those filaments. Our position in it helps explain why certain galaxies are nearby and why certain empty regions exist around us. The filament doesn't feel like anything physically. If you travelled through it, you wouldn't notice the shape, but the gravitational environment defines the motions of everything within it. The cosmic web connects superclusters across enormous distances, linking them even when no obvious visual boundary exists. One of the reasons astronomers study these patterns is because they reveal where the heavier structures are. Clusters and superclusters form at the intersections of filaments, where matter accumulates over long periods. The Shapley Supercluster sits at one of these intersections. To understand Shapley properly, we have to understand how matter tends to gather and how those gatherings influence everything around them. Our cosmic neighbourhood is one example. Even though it's large, it's only one part of a far bigger layout, one that stretches far beyond Laniakea's borders. Right now, though, we're still grounding ourselves within the region we can connect to directly. The Milky Way, the local group, the local sheet, Laniakea, the flows of galaxies, the patterns of motion that show us where the heavier concentrations of mass must be. And among those heavier regions, the Shapley concentration stands out not just as a point of interest, but as a dominant source of gravitational pull. When you look at maps of our local universe created from surveys of galaxy motion, you see the same theme appear again and again. The Milky Way is drifting with the local group. The local group is moving with the local sheet. Larger regions are all leaning ever so gently toward a direction that points beyond the great attractor. Even though it's distant, Shapley's mass adds to the pull, shaping the flow lines like a heavy anchor shaping the curvature of a stretched sheet. This idea helps bridge the gap between where we are and where we're heading next. But before we step outward to that remarkable destination, there's still room to settle into the feeling of our present location, because knowing the layout of our surroundings changes how we approach what lies ahead. When we think of home, we generally imagine a familiar setting, a bedroom, a chair, a place where we sit. But on cosmic scales, home becomes a layered structure. Each layer reassures us that the universe is organized in ways we can understand. Each layer connects us to the next. We're not floating in isolation. We're part of a structure that extends outward in coherent steps. When we talk about something as enormous as the Shapley Supercluster, it helps to pause and get clear on what a supercluster actually is. The word itself sounds straightforward enough, but in astronomy it describes something with a very specific meaning, and that meaning only becomes easy to grasp when we look at it calmly and at a measured pace. A supercluster is one of the largest known structures in the universe, but calling it large doesn't really do much for our understanding. Everything out there is large compared to us. What matters more is understanding how superclusters fit into the overall arrangement of the cosmos, why they exist, and what makes them different from the things we're used to hearing about like galaxies or galaxy clusters. Most people are familiar with the idea of a galaxy. Our Milky Way is one, Andromeda is another. Galaxies are vast collections of stars, gas, dust, dark matter and other material all bound together by gravity. They can range from small dwarf galaxies with only a few 100 million stars to giant spirals and ellipticals containing trillions. A galaxy is enormous compared to anything we experience directly, but in the large-scale structure of the universe, a galaxy is more like a basic element, a building block. Clusters of galaxies are the next step up. They're groups of galaxies bound together by gravity, often containing dozens to hundreds of galaxies, sometimes more. These clusters are held together by large amounts of dark matter and filled with hot gas that emits X-rays detectable by space telescopes. In a typical galaxy cluster, the galaxies move around a shared center of mass, interacting gravitationally over millions of years. These clusters are far larger than individual galaxies and represent some of the densest regions of the cosmic web. If we stopped the explanation here, it might feel manageable. A galaxy is a collection of stars. A galaxy cluster is a collection of galaxies. But a supercluster isn't simply a larger cluster. It's not just a bigger version of the same idea. It's something more complex. Something that sits at a scale where gravity and the expansion of space start competing in subtle ways. Understanding a supercluster means understanding that at this level, the universe behaves differently. Structures don't stay tightly bound together in the same way that galaxies do within clusters. The distances involved are so vast that the pull between different parts of a supercluster may not be strong enough to keep everything permanently connected. A supercluster is a broad gathering of galaxy clusters, galaxy groups and cosmic filaments that all occupy the same general region of space. They move in related ways. They share common gravitational influences. They sit within a larger flow pattern shaped by the distribution of mass around them. But they're not held together in a firm, rigid structure. Instead, they form a loose, extended region where matter has collected over billions of years due to slight variations in the density of the early universe. One way to think about superclusters, without slipping into imagery that feels too poetic, is to imagine that they describe areas where galaxies and clusters are more densely arranged than average. They're not walls or islands or anything with a solid shape. They're regions, very large regions. They stretch across tens or hundreds of millions of light years. But even though they're enormous, they're not isolated from one another. They sit on the cosmic web, connected to other regions through filaments. These filaments are thinner structures where galaxies form long chains, sometimes hundreds of millions of light years long, linking one supercluster to another. What makes superclusters meaningful in cosmology is that they show the universe has structure at every scale we can observe. The distribution of galaxies is not uniform, it's not random. It follows underlying patterns laid down shortly after the Big Bang. The slightly denser areas became more and more pronounced over time, gathering matter through gravity, while the less dense areas became cosmic voids. Superclusters are the broad peaks of those density patterns. They're the largest visible signs of how matter arranged itself as the universe expanded. But as soon as we reach this scale, something interesting happens. Gravity isn't strong enough to hold an entire supercluster together in a fully stable way. The expansion of the universe stretches everything. On the scale of galaxies and clusters, gravity can win. It can bind things tightly. But at the size of superclusters, expansion becomes significant enough that many parts of a supercluster will eventually drift apart over billions of years. They're currently moving together or influenced by similar forces, but they aren't permanent in the way that smaller structures are. Some astronomers have even argued that the word supercluster can be misleading because it makes them sound like single-bound objects. They're not. They're better described as extended regions defined by flows of galaxies, concentrations of mass, and large-scale patterns of matter. Our own region, Laniakea, is an example of this. It contains many clusters and groups, including our local group, but there is no outer wall, no visible boundary, no single center the way a galaxy cluster has. The defining feature of Laniakea is the pattern of motion. Galaxies in this region tend to flow toward a certain gravitational basin, and that basin helps define the supercluster's extent. The Shapley Supercluster too is not held together as a compact object. Instead, it represents a vast region where many clusters and filaments have collected, forming an exceptionally large and dense concentration of mass. Superclusters come in many shapes and sizes. Some are relatively modest, some are elaborate, and a few, like Shapley, are so massive that they reshape how astronomers think about structure formation in the universe. To understand why Shapley stands out, it helps to look at how superclusters are typically identified. Astronomers map galaxies across the sky. They measure their distances using redshift, which tells them how fast galaxies are moving away due to the expansion of the universe. By combining these measurements with observations of brightness, shape, and distribution, they build three-dimensional maps of where galaxies are located. When these maps are assembled, patterns emerge. Instead of a uniform distribution, astronomers see clusters, filaments, walls, and voids. Superclusters appear as extended regions of enhanced galaxy density, connected through filaments and containing multiple substructures. They're not all equally dense. Some have clear high-density centers where massive clusters sit. Some are more diffuse. Some appear stretched across unusual shapes, depending on how the matter in that region formed over time. An important thing to remember is that these structures didn't form instantly. The early universe was almost uniform with tiny variations in density. Over billions of years, gravity amplified those variations. Areas with slightly more matter collected more, gradually forming galaxies and clusters. Areas with slightly less matter became voids. Superclusters represent the highest peaks in this landscape. They grew from the most significant early density fluctuations. But because expansion gradually spreads everything apart, only smaller portions of them will remain gravitationally bound in the far future. This understanding is essential when trying to grasp what makes Shapley so remarkable. It isn't just big, it's unusually dense. In many regions of the universe, superclusters have loosely defined centers, or several clusters spread across large distances. Shapley contains some of the most massive galaxy clusters known, many of them packed into a concentrated region. This level of mass stands out compared to most other superclusters. It's not just a large area, it's a large area with clusters of exceptional size and gravitational influence. When astronomers classify structures, they use measurements like mass, galaxy density, cluster richness, and total luminosity. Across these metrics, Shapley lands at the extreme end. It contains dozens of particularly massive clusters and hundreds of smaller galaxy groups. Its total mass is so high that it noticeably affects the motion of galaxies far outside its immediate region. This influence contributes to the flow patterns within Laniakea, creating a link between our home region and something hundreds of millions of light years away. But before focusing entirely on Shapley, it helps to stay grounded in the broader definition. A supercluster isn't a single thing, it's a combination of components. It contains clusters, which are the largest gravitationally bound systems in the universe. It contains groups, which are smaller collections of galaxies like our local group. It contains filaments, which are long stretches of galaxies forming bridges between clusters. And it sits within the cosmic web shaped by dark matter distribution. All of these pieces interact gravitationally. They form a pattern that is visible in surveys and helps define one region from another. The cosmic web is crucial here. Without it, the idea of a supercluster wouldn't make sense. Galaxies would be randomly scattered, and no large-scale structure would exist. But the web, formed by dark matter and amplified by gravity, naturally produces interconnected regions of varying density. Superclusters sit at these intersections. Their sizes can range widely. Some span 100 million light-years, some extend much farther. Their complexity varies. Some are sprawling and irregular. Others are concentrated around a few strong clusters. Shapley is one of the most concentrated examples ever observed. Another important point is that superclusters help scientists trace the history of the universe. By studying their shapes, masses, and distribution, researchers can test models of cosmic evolution. If structures like Shapley were extremely common, it would suggest that density fluctuations in the early universe were much larger than current models predict. Instead, Shapley is unusual, which helps confirm that most regions formed with different characteristics. Understanding it helps refine our theories of how matter gathered over time. When thinking about superclusters, it's also useful to consider that they're not isolated regions of perfect stability. Everything inside them is moving. Clusters move relative to one another. Filaments stretch and shift slowly over billions of years. Galaxies glide through them under the pull of gravity. The entire structure is shaped by ongoing change, but the changes occur so slowly that they only become noticeable on cosmic timescales. Nothing within a supercluster is static. Even the densest regions evolve. Galaxies collide in clusters. Gas heats and cools. Dark matter settles into new distributions. These motions help define what we see today. The reason the Shapley supercluster stands out so strongly is because it pushes the limits of what superclusters typically look like. Most superclusters are large but relatively diffuse. They contain a few prominent clusters and many smaller ones spread across a wide area. Shapley, by contrast, contains an unusually high number of very massive clusters packed into a relatively concentrated section of space. Its density makes it one of the strongest gravitational regions in the observable universe on these scales. Before we move on, it's helpful to repeat one grounding idea. A supercluster is not a single-bound object. It is a large region defined by patterns of galaxies, clusters, and motions shaped through cosmic history. What we call a supercluster is simply the region where these features gather, and Shapley is one of the strongest examples of such a gathering. Understanding what a supercluster is helps prepare us for understanding why Shapley is such an important one, and why astronomers spend so much time studying its mass, its layout, and the influence it has across hundreds of millions of light years. It's sometimes surprising to learn that the universe hides its largest influences in places where nothing looks particularly unusual at first glance. The brightest objects in the night sky aren't the ones that shape the largest movements of galaxies. The real power in the cosmos tends to come from regions we can barely see without careful instruments. These are the hidden giants of the cosmic web, massive structures that stretch across space and hold galaxy clusters together through gravity so steady and widespread that it operates over hundreds of millions of light years. They don't shine, they don't announce themselves, yet they guide the motion of entire regions of the universe with a strength that becomes clearer only when we step back far enough to see the larger patterns. The idea that these enormous structures exist came slowly. Astronomers didn't immediately realize that galaxies form patterns on such large scales. When the first galaxy catalogues were being assembled, the focus was mostly on identifying shapes, measuring distances, and figuring out how far the universe extended. The notion that galaxies might not be sprinkled randomly across space wasn't obvious at first. It took decades of surveying skies, comparing positions, and mapping out enormous areas before a larger picture started to emerge. As these maps expanded, astronomers saw something unexpected. Galaxies seemed to gather, not just in small clusters or pairs, but in extended formations stretching far across the observable universe. These arrangements didn't look like anything familiar from everyday experience. They weren't smooth, they weren't evenly spaced. Instead, they arranged themselves into connected strands and nodes. Over time, these became known as filaments, walls, and clusters. Together, they formed what we now call the cosmic web. This web isn't something you would see if you looked out of a spaceship window, even if you were travelling at impossible speeds. It's only visible when you plot the positions of millions of galaxies in 3 dimensions and look at the entire map at once. From that vantage point, the structures become astonishingly clear. Long threads connect distant areas, dense nodes anchor everything, and between these patterns lie enormous voids, regions with very few galaxies. Within this sprawling network, certain places stand out as particularly massive. These are the hidden giants. They don't shine brightly on their own, because brightness comes from stars and gas, and those elements don't always gather at the same density as mass. Instead, the giants reveal themselves through gravity. The pull they exert on everything around them is strong enough to influence galaxy motions over enormous distances. They quietly guide the direction of galaxy clusters, the flow of filaments, and the overall shape of their surrounding regions. One of the key ideas that helps explain these giants is that matter in the universe didn't spread evenly after the Big Bang. Tiny variations in density existed from the very beginning. Some areas contained slightly more matter, some contained slightly less. These small differences grew over time. Gravity pulled material toward the denser regions, making those areas even more significant. Meanwhile, sparser regions became emptier. This long-term process created the cosmic web, with its interconnected structures shaped by billions of years of cosmic evolution. The hidden giants are the peaks of this distribution. They're the regions where matter gathered most intensely. They contain vast amounts of dark matter, hot gas, and galaxies locked into long-term gravitational relationships. If you were able to place a marker on the largest structures in the universe, the giants would be the first places you'd identify. They're the hubs, the intersections where many filaments meet. They serve as anchors for the cosmic landscape, exerting influence in every direction. Our own region is shaped by one of these giants. The Great Attractor, located relatively nearby in cosmic terms, is a broad area of high mass concentration that affects how galaxies in our surroundings move. The name makes it sound like a single object, but it's not. It's a region with several clusters and large amounts of dark matter spread across tens of millions of light years. It doesn't stand out visually. If you look toward it with the naked eye, you wouldn't see anything unusual, but measurements of galaxy motions reveal its presence unmistakably. Galaxies across our region, including the Milky Way, drift in its direction. This drift isn't fast enough for us to feel, of course. Everything happens over timescales far beyond anything we experience. You could stand still for your entire life, and the galaxy's movement wouldn't show itself in any direct way. But astronomers detect it by measuring redshifts, brightness, and motions relative to the cosmic microwave background. These measurements reveal a pattern. Our galaxy is moving toward a specific direction, and that movement aligns with the gravitational pull of massive structures, including the hidden giants deep within the cosmic web. But the great attractor isn't the only one influencing us. Over time, it became clear that something even larger exists beyond it. As astronomical surveys improved, deeper observations revealed an even more substantial concentration of matter farther away. These discoveries led to the recognition of the Shapley Supercluster, a region whose mass outstrips nearly every other known structure. Shapley isn't a single cluster. It's a vast region containing dozens of extremely massive galaxy clusters, connected through filaments, all sitting within a dense basin of dark matter. Its gravitational influence is so strong that it contributes significantly to the motion of galaxies in our entire local region. To understand how something so distant can affect us, it helps to pause and consider the quiet strength of gravity. Even though gravity weakens with distance, it never truly stops. On cosmic scales, even a subtle pull becomes meaningful when it comes from a structure containing hundreds of trillions of solar masses. If you think about a tug-of-war spread over hundreds of millions of light years, the Shapley region is one of the major teams pulling on the rope. It doesn't dominate everything, but it adds enough force that astronomers can measure its influence through the way galaxies drift in that direction. What makes these giants difficult to detect is that they're not always in regions of the sky where observations are easy. Some lie behind the dusty disk of our Milky Way, in what astronomers call the zone of avoidance. Dust and stars block the view in visible light, making it hard to detect galaxies behind them. But infrared surveys, radio observations, and X-ray studies help fill in the gaps. Over time, these techniques revealed that large portions of the cosmic web extend into areas that early observations simply couldn't reach. Once these hidden areas were mapped, the giants began to show their full shapes. Another reason they can be difficult to detect is that the most massive parts of these structures don't necessarily emit much light. Dark matter makes up the majority of the mass. It doesn't shine, doesn't reflect, and doesn't interact with light. So the true heft of a structure only becomes clear when astronomers study the motions of galaxies and measure how much mass is required to produce those motions. It's a bit like noticing that a ship is drifting toward a region of ocean where nothing seems visible on the surface. The movement tells you something is there even before you can identify the shape of what lies beneath the water. Galaxy clusters help reveal the hidden giants as well. The most massive clusters are usually located in or near these regions. They contain thousands of galaxies, huge quantities of hot gas, and enormous dark matter halos. These clusters shine brightly in X-rays due to the heated gas, and their gravitational lensing distorts the light of background galaxies, creating arcs that astronomers can measure. These signs provide clues to the concentration of mass in a given region. When many such signs appear close together, it becomes clear that something significant is present. The Shapley Supercluster includes some of the most substantial examples of these massive clusters. They're not scattered randomly. They sit in a region where the cosmic web's filaments converge. This convergence acts like a collecting basin for matter. Over billions of years, gravity drew material toward these intersections, building up the mass we now observe. The same process has occurred across the universe, but some regions ended up with far more matter than others. Shapley is one of these exceptional areas, an example of how variations in density from the early universe resulted in structures far beyond the average scale. When astronomers study these giants, they're not only mapping the present-day universe, they're also learning about the past. These structures are fossil records of conditions that existed when the universe was young. By comparing the masses, distributions, and shapes of superclusters and filaments, scientists test theories about how matter behaved shortly after the Big Bang. If certain types of structures are too common or too rare, it can indicate that our understanding of early density fluctuations needs adjusting. The hidden giants provide strong constraints for these models because their existence requires large initial variations in density. But if those variations had been too large, the universe wouldn't look the way it does now. Achieving the right balance is one of the reasons cosmology involves so much careful measurement. The giants also offer clues about the future. As cosmic expansion accelerates due to dark energy, large-scale structures will gradually stop interacting gravitationally in the ways they do today. Over extremely long periods, galaxies outside our local region will drift away faster than gravity can pull them together. The largest giants will remain internally coherent to some extent, but even superclusters will eventually be affected by expansion. The cosmic web will thin, filaments will stretch, and distant regions may no longer exert influence on one another. But for now, the giants remain significant features in the observable universe, shaping the motions we can measure and giving form to the structures we study. The quiet strength of these giants makes them essential for understanding the Shapley Supercluster. Shapley doesn't exist in isolation. It's part of a larger pattern. Its immense mass is tied to filaments that connect it to other clusters. Its influence reaches outward into regions far beyond its boundaries, and its role as one of the most massive known structures allows it to shape the motions of galaxies across hundreds of millions of light years. The first hints of the Shapley region didn't appear as a dramatic revelation or a sudden breakthrough. They surfaced quietly, almost unnoticed, in early galaxy surveys that were far smaller and less detailed than anything we have now. Astronomers of the early 20th century were still learning how galaxies were arranged in space, and many of the tools we rely on today didn't exist yet. Photographic plates, careful visual inspections, and hand-drawn catalogues formed the foundation of our understanding. Even with those limited methods, certain areas of the sky began to stand out as unexpectedly rich in galaxies. One of those areas later became known as the Shapley concentration. At the time, however, it was simply an interesting patch of the sky filled with faint smudges that seemed to gather more densely than usual. It didn't attract immediate attention. Astronomy was still coming to terms with the idea that the Milky Way wasn't the entire universe. Only a few years earlier, debates had taken place over whether spiral nebulae were distant galaxies or nearby objects within our own system. As that debate settled, the focus shifted toward measuring distances and understanding the large-scale structure around us. Researchers weren't yet looking for superclusters. They didn't know such structures existed. They were simply cataloguing galaxies to understand how many there were and where they might be found. The early photographs of the Shapley region didn't look unusual at first. They were crowded with galaxies, but many areas of the sky were crowded. It took someone examining the plates with enough attention to notice that this particular region contained not just a few clusters but several unusually rich ones. That someone was Harlow Shapley, an astronomer already known for his work on mapping the Milky Way. He had helped determine the size of our galaxy and the location of the Sun within it. His earlier work dealt with star clusters and the distribution of objects on a much smaller scale. But when he turned his attention to galaxies beyond the Milky Way, he noticed something intriguing. In 1930, Shapley and colleagues identified a concentration of galaxy clusters in the direction of the constellation Centaurus. They didn't yet have distance measurements for all of them. They didn't know how far away the region was or how massive it might be. They only saw that several rich clusters seemed to gather in one broad area, far more than would be expected if galaxies were distributed randomly. Without modern tools, it was difficult to interpret this finding. Still, the clustering was unusual enough to be recorded and later referenced in studies of galaxy distribution. At that time, the idea that enormous structures could exist across hundreds of millions of light years was still distant. Even galaxy clusters were not fully understood. Researchers could only work with small slices of the sky. They measured brightness, counted objects, and slowly added to catalogues. The true scale of the universe was still being uncovered, and the recognition of extremely large structures would require surveys that could observe deep and wide enough to form a three-dimensional map. For decades after Shapley's observations, this region appeared in astronomical papers, but it wasn't recognized as anything extraordinary. It was noted for its richness, its many clusters, and its relative concentration. But no one had yet measured its full extent. Without reliable redshift measurements, it was difficult to determine which clusters belonged to the same structure and which were simply overlapping along the line of sight. Two clusters could appear close together on the sky while being separated by vast distances in depth. Until redshift surveys improved, the true nature of this region remained uncertain. The turning point arrived when galaxy surveys expanded significantly in the late 20th century. Redshift measurements allowed astronomers to determine how fast galaxies were receding due to the expansion of the universe, which in turn provided distance estimates. Patterns began to emerge that couldn't be seen before. When astronomers plotted galaxies not only by their position on the sky, but also by their distances, the Shapley region stood out dramatically. Clusters that had appeared close together in earlier observations turned out to be part of a massive concentration spanning a huge volume of space. What had once looked like a modestly interesting region became a structure of impressive scale. The concentration contained numerous rich clusters, each containing thousands of galaxies and many smaller groups surrounding them. More than that, the clusters weren't scattered randomly. They were arranged in a pattern consistent with filaments and nodes of the cosmic web. The region formed a dense node where several filaments converged, gathering enormous amounts of matter. As the data accumulated, astronomers realized that this structure wasn't just large, it was unusually massive. Estimates of its total mass increased as more clusters were identified and measured. The Shapley region stood out as one of the most massive concentrations of galaxies in the nearby observable universe. Its gravitational influence extended far beyond its immediate location. It wasn't simply a local feature. It played a role in shaping the flow of galaxies on scales extending hundreds of millions of light years. The recognition of this influence took time. Astronomers studying the motion of galaxies in our region noticed that the Milky Way and many nearby galaxies weren't drifting randomly. They were moving toward a specific direction at speeds higher than expected from local gravitational fields alone. This motion is known as the peculiar velocity of our galaxy, and it puzzled researchers for many years. The Great Attractor had been identified as one source of this motion, but the numbers still didn't fully add up. The pull from that region wasn't strong enough to explain the observed drift. As deeper surveys looked beyond the Great Attractor, the Shapley concentration emerged as a likely contributor. Its mass was so significant that it could account for a substantial fraction of the observed motion. The realization that a structure so far away could influence our galaxy underscored just how massive it must be. Its presence added new layers to the understanding of large-scale cosmic flows. The discovery didn't come from a single observation. It came from decades of data gathering, distance measurements, and improved mapping techniques. Improved observations also helped reveal the shape of the structure. The Shapley region isn't a compact sphere of clusters. It spans more than 100 million light-years and contains interconnected filaments stretching outward. These filaments feed into a dense central concentration that holds numerous rich clusters. Some of these clusters are among the most massive known. Their central galaxies are enormous, surrounded by hot gas and extended halos of dark matter. X-ray observations confirmed the presence of this hot gas, which reaches temperatures of millions of degrees, a signature of extremely massive cluster environments. As astronomers observed the region in more detail, they also identified smaller substructures. Groups of galaxies that might seem insignificant on their own contribute to the overall mass. The combined effect of many such groups adds to the gravitational pull of the Shapley concentration. These findings reinforce the idea that the structure was not just large in area but dense in content. Density matters because it determines how much gravitational influence a region can exert. The Shapley region's density is one of the reasons it stands apart from most other superclusters. Another factor that complicated early observations is the location of the Shapley concentration in the sky. Part of it lies near the zone of avoidance, where the Milky Way's dust and stars obscure the view. This made it difficult to map all the galaxies in the region in visible wavelengths. Infrared and radio surveys later helped fill in these gaps, revealing galaxies that had been hidden behind interstellar dust. As these surveys became more complete, the full extent of the Shapley structure became clearer. The more complete the map, the more obvious the region's scale and significance became. Modern surveys, including large projects such as the 2DF Galaxy Redshift Survey, the 6-Degree Field Galaxy Survey, and others, have provided increasingly detailed views of the region. With each new set of measurements, the Shapley concentration appears even more substantial. It contains over 20 major galaxy clusters and many smaller ones, all arranged in a broad region with substantial mass concentrations. These clusters are not merely neighbours, they form a connected structure that stands as one of the most massive features in the cosmic web. The recognition of Shapley's importance didn't happen all at once. It grew as new technologies allowed astronomers to see deeper, measure more precisely, and map the universe in greater detail. The tools expanded, observations expanded, the understanding expanded. Each improvement brought more clarity, and the picture of Shapley shifted from a curious patch of sky to one of the defining features of the local universe. It became clear that this structure wasn't just a statistical anomaly. It was a natural result of cosmic evolution in a region where early density variations were particularly high. As these discoveries unfolded, the mystery of the Shapley concentration shifted from one of identification to one of interpretation. How did such a massive structure form? What does it mean for our understanding of a large-scale cosmic evolution? How does it compare to other massive structures such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall? Answering these questions requires both detailed observations and theoretical models. In many respects, Shapley serves as a key test case for understanding how matter organizes itself on the larger scales. The gradual uncovering of this structure, from Shapley's first observations to modern three-dimensional maps, shows how astronomy often advances not through sudden revelations, but through the accumulation of careful work. Each survey builds on the previous one. Each new technique reveals more detail. Each improved measurement clarifies what lies hidden behind distance, dust, and the limitations of earlier tools. The process can be slow, but the results reveal structures far beyond anything that early astronomers could have imagined. There comes a point when looking at the Shapley region where the usual vocabulary of astronomy stops being useful. Terms like large, dense, or massive feel too ordinary for what the observations reveal. Even supercluster, a word already meant to describe something enormous, starts to sound insufficient. The Shapley concentration sits at the far end of the scale of known structures in the nearby universe, pushing against the upper limits of what cosmic structure formation theories predict. This is what makes it a supercluster beyond superlatives. Studying it means confronting the difference between something that is simply big and something that stands so far above the average that it reshapes the way astronomers think about the distribution of matter. To understand why Shapley reaches this category, it helps to begin with the numbers, even if the numbers themselves become difficult to visualize. The structure spans roughly 200 million light-years, though the exact boundaries are not sharply defined. They are shaped by the distribution of clusters and the filaments that connect them. Within this region lie more than 20 very massive galaxy clusters and numerous smaller groups. Some of these clusters rank among the most massive ever catalogued, containing thousands of galaxies each and enormous quantities of dark matter. The combined mass of the Shapley concentration is estimated to reach well over 10 quadrillion times the mass of the Sun. Some studies place it even higher depending on how the boundaries are drawn and which clusters are included. But the size alone is only one part of the story. What truly sets Shapley apart is its density. Many superclusters stretch across similar distances, but they rarely contain such a high concentration of massive clusters in such a compact area. Most superclusters are relatively loose structures, shaped more by flows than by strong localized gravitational basins. Shapley, by contrast, contains a dense central region filled with large clusters arranged unusually close to one another. This density matters because it determines how much gravitational influence the region can exert. The more mass that lies in a given volume, the stronger its pull, and in Shapley's case, the gravitational basin is deep enough to affect galaxy flows across extraordinary distances. This leads to another unusual feature. Shapley contributes significantly to the peculiar velocities of galaxies far outside its borders. Peculiar velocity refers to the motion of a galaxy relative to the general expansion of the universe. Most galaxies drift apart due to expansion, but local motions overlay this general trend. When astronomers mapped these motions in our region, they found that many galaxies, including the Milky Way, are moving toward the same general direction. Initially, the Great Attractor was thought to be the primary cause, yet as measurements improved, it became clear that the Great Attractor alone could not account for the observed velocities. Something more massive had to be pulling on entire sections of the cosmic web. Shapley provides a major portion of that missing mass. Even though it lies hundreds of millions of light-years away, its gravitational influence is strong enough to contribute to the motion of our galaxy. This influence doesn't operate in the sense of pulling us rapidly toward it. Instead, it adds a subtle, long-term component to our movement through space. Galaxy motions on these scales are slow and gradual, but over hundreds of millions of years, even a small additional drift becomes meaningful. The fact that Shapley can contribute to such motion from such a distance underscores just how massive it must be. Another factor that places Shapley beyond ordinary descriptions is the richness of its cluster population. Galaxy clusters are not evenly distributed across the universe. Many regions contain few or none, some contain a handful, very few contain multiple rich clusters. Shapley contains dozens. Among them are clusters like Abell 358, Abell 342, and others in the core region. These clusters are not moderately sized, they are heavyweights. Each cluster holds thousands of galaxies and massive halos of dark matter. They contain hot gas heated to tens of millions of degrees, emitting X-rays detectable by space telescopes. This hot gas alone can weigh as much as all the stars in hundreds of galaxies combined. The fact that so many such clusters occupy the same region is what makes Shapley stand out so dramatically. To appreciate the weight of these clusters, consider that the largest galaxy clusters known can weigh over 1,000,000 billion times the mass of the Sun. Clusters of this scale don't appear in just any part of the universe. They form in regions where early density fluctuations were unusually high. That Shapley contains so many of them suggests that this region began its development from one of the largest early fluctuations, a patch of the young universe that contained significantly more matter than the surrounding areas. Over billions of years, gravity amplified this initial difference, drawing material into the region and forming the structure we see today. In addition to its extraordinary mass, the Shapley region also contains complex internal structure. It's not a single clump. It has multiple substructures connected by filaments. Some of these filaments extend outward toward other clusters that may not be officially counted as part of the Shapley concentration, but still interact with it gravitationally. The region also includes bridges that connect it to surrounding structures, forming a transition between the densest central areas and the more diffuse outskirts. These details make Shapley not just large but intricate. Its internal arrangement resembles a miniature version of the cosmic web, except that in this case the miniature version spans hundreds of millions of light years. Another exceptional aspect is how Shapley compares to other superclusters. For example, the Virgo supercluster, of which our local group is a part, is larger by volume but far less dense. The Coma supercluster contains some massive clusters but does not reach the same combined mass as Shapley. Other well-known structures such as the Hercules supercluster or the Perseus-Pisces region are impressive but still fall short in total mass or concentration. Shapley remains one of the heaviest known structures in the nearby universe, and few regions approach it closely. This exceptional mass makes Shapley an important region for cosmological research. Theories of structure formation predict limits on how large and dense superclusters can be, based on the initial conditions of the universe and the behavior of dark matter over time. Shapley tests those limits. If structures like Shapley were extremely common, it would imply that the early universe had larger density fluctuations than current theories allow. But the fact that it is unusual supports the idea that most regions evolved from smaller variations. Shapley sits near the upper end of the spectrum, but not so far out that it contradicts existing models. Instead, it serves as a benchmark for understanding what the most extreme natural structures look like. The hidden presence of dark matter also plays a crucial role. Most of the mass in Shapley is dark matter, not stars, gas, or visible galaxies. Astronomers can't see it directly, but they detect it through gravitational lensing and the motions of galaxies within clusters. The amount of dark matter required to explain these motions is enormous, far outweighing the visible matter. Without such dark matter, the structure could not hold together as well as it does. Its clusters would not contain as many galaxies, and the gravitational pull on surrounding regions would be far weaker. By measuring the velocities of galaxies within Shapley's clusters, astronomers estimate the mass of the dark matter halos that envelop them. These halos extend far beyond the visible boundaries of the clusters, forming the true backbone of the structure. Hot gas provides another method of measurement. In massive clusters, gas becomes heated to extreme temperatures through gravitational compression. This gas emits X-rays, which telescopes such as Chandra and XMM Newton can detect. The brightness and distribution of this X-ray emission allows astronomers to estimate the mass of the clusters. Shapley's clusters show intense X-ray emissions consistent with their high mass. Many of these clusters rank among the brightest in the X-ray sky, reinforcing the idea that the region is one of the densest known. Even with all this mass, Shapley is not gravitationally bound in the same way that smaller structures are. The expansion of the universe pulls everything apart over large enough distances. Only structures below a certain size remain tightly bound over long periods. Superclusters sit at the boundary between bound and unbound systems. Parts of Shapley, especially its densest central regions, will remain gravitationally connected for billions of years. Other parts will eventually drift apart as cosmic expansion accelerates. This dynamic boundary is another reason superclusters can be difficult to define clearly. Their extent depends not only on the current distribution of matter, but also on the forces that act across vast distances. The Shapley region continues to challenge astronomers today. New surveys extend deeper into the area, revealing more galaxies and clusters. Some discoveries refine the boundaries of the structure. Others identify new subclusters or filaments. Even after decades of study, the map of Shapley is not completely finished. As instruments improve, the structure becomes even more detailed. It shows complexity that earlier surveys simply couldn't detect. Its role in shaping motions across Laniakea adds another layer of significance. The flow of galaxies toward Shapley tells astronomers not only about the mass of the structure, but also about the mass distribution in the entire surrounding region. These flows form part of the cosmic velocity field, a map of how galaxies drift relative to the overall expansion of space. Without Shapley, the velocity field in our region would look very different. Understanding these motions helps astronomers build models of how structures grow and evolve over cosmic time. What makes Shapley remarkable, then, is not simply its size, density, or influence, but the fact that all of these characteristics come together in one region. Many superclusters are large. Many contain rich clusters. Many influence the motion of galaxies, but few combine all these properties so strongly. Shapley stands at an intersection of mass, density, structure, and gravitational impact that places it among the most extreme known structures in the nearby universe. Most of what we know about the universe's largest structures becomes clear only when we start paying attention to motion. Not the fast kind that happens in daily life, but motion so slow and steady that they reveal themselves only through careful measurement. The Shapley region is one of the best examples of this. Its immense mass doesn't announce itself through brightness or shape. It reveals itself through the way entire regions of space are drifting. When astronomers map out these motions, a picture emerges of a vast gravitational gathering, a place where the combined pull of countless clusters and dark matter creates a long-range influence stretching across hundreds of millions of light years. To understand this influence, it helps to begin with the idea of cosmic expansion. On the largest scales, everything in the universe is moving apart as space itself expands. This expansion doesn't depend on galaxies pushing away from each other. Instead, it is driven by the expansion of the fabric of space between them. Over these distances, space grows, and objects become farther apart simply because the underlying structure increases. Against this general expansion, the effect of gravity creates local motions that deviate from the expansion rate. These motions are what astronomers call peculiar velocities. They are the small but meaningful differences between the expected expansion motion and what is actually observed. Shapley's influence becomes visible through these peculiar velocities. Galaxies in our region of the universe are not drifting randomly. They're moving toward an area of the sky that aligns with the direction of the Shapley concentration. This movement isn't freefall, and it isn't rapid enough to be felt or directly seen. Instead, it appears as a long-term trend. When astronomers measure galaxy redshifts across thousands of systems, they find a common component in their motion. That component shows up as a shared drift, indicating that many galaxies are responding to the same gravitational pull. This drift is not dominated by Shapley alone. Several massive structures contribute to it. However, once the influence of the great attractor and nearby clusters is accounted for, a significant portion of the remaining motion points toward the Shapley region. Its mass is large enough to create a basin in the surrounding cosmic landscape, a region where the gravitational potential is lower than average. Galaxies tend to move toward lower potential areas over time, and Shapley's basin reaches far beyond its borders. One of the reasons Shapley exerts such an impressive pull is the number of massive clusters within it. Each cluster contributes its own gravitational field. When many such fields overlap, the combined effect becomes substantial. Dark matter halos surrounding these clusters extend far beyond the visible galaxies. These halos, which contain the majority of the mass in each cluster, overlap and connect, forming a large gravitational landscape. This landscape acts like a gradual slope that galaxies move down over cosmic timescales. Cluster masses are typically measured through the velocities of the galaxies they contain. The faster galaxies move within a cluster, the more massive that cluster must be to keep them from escaping. In the Shapley region, the velocities recorded within several clusters are extremely high. This indicates dark matter halos of exceptional mass. These halos push Shapley into a category of structures whose gravitational potential is deep enough to have measurable effects across vast distances. X-ray observations reinforce these findings. Very hot gas fills the central regions of large clusters. The temperature of this gas corresponds to the depth of the cluster's gravitational potential. Shapley's clusters show exceptionally high temperatures, sometimes exceeding tens of millions of degrees. This level of heat suggests that the gas has settled into deep gravitational wells, which means the clusters must contain enormous amounts of matter. When several such clusters lie in close proximity, their combined gravitational field becomes one of the strongest detectable on local cosmic scales. Beyond the clusters themselves, the filaments surrounding Shapley contribute significantly to its overall mass. Filaments are not uniform. They contain varying densities of galaxies and dark matter, but some filaments in the Shapley region are especially thick. These filaments act as bridges across the cosmic web, channeling matter toward the clusters over billions of years. As material flows along these filaments, clusters grow larger, increasing the total mass of the region and deepening the gravitational basin. Peculiar velocity studies help quantify this effect. By subtracting the expected expansion velocity from observed velocities, astronomers isolate the motion caused by gravity. When these peculiar velocities are mapped across large sections of the sky, a pattern becomes clear. Galaxies in several directions show coherent flows toward the Shapley region. The coherence of these flows is important. If galaxies moved randomly, the velocity field would not show a preferred direction. Instead, the data show an organized drift, suggesting that Shapley plays a significant role in guiding large-scale motion. This gravitational influence doesn't operate alone. The universe is filled with structures, and many of them contribute to the velocity field. The Great Attractor adds its own pull. The Laniakea Basin shapes the local flow. Other superclusters and filaments exert their influences as well. But despite this complexity, Shapley stands out because of the scale of its effect. Many studies find that a substantial portion of the motion of galaxies in our cosmic neighborhood cannot be explained without including Shapley's mass. Its gravitational influence appears to be among the most significant contributors in our region. The interaction between expansion and gravity becomes more intricate when superclusters are involved. Expansion works to separate distant regions, while gravity works to draw them together. On small scales, gravity dominates completely. On very large scales, expansion becomes the stronger force. Superclusters sit in a range where both forces are relevant. Parts of Shapley may remain gravitationally connected for many billions of years. Other parts may eventually drift apart due to expansion. But for now, the gravitational force is strong enough to shape galaxy flows. The balance between gravity and expansion is part of what makes Shapley important in cosmology. It represents a boundary case, a structure large and dense enough that its gravitational effects can be measured over enormous distances. Understanding how Shapley formed provides insight into why its pull is so strong. The early universe contained small fluctuations in density. Shapley formed in a region where these fluctuations were larger than average. Over time, gravity amplified these differences. Matter flowed towards slightly denser areas, causing them to grow. As they grew, their gravitational influence increased, drawing in more matter and accelerating their development. The result was a structure that developed into one of the most massive regions in the nearby universe. The gradual process of matter flowing into dense regions is known as hierarchical structure formation. Shapley exemplifies the upper end of this process, showing what happens when an initially dense region accumulates vast amounts of material over cosmic time. One of the most informative tools for studying these motions is the cosmic microwave background. Tiny variations in temperature across this background serve as a reference for measuring the motion of galaxies relative to the ancient light that fills the universe. These measurements indicate that our galaxy, along with many others, is moving with a significant peculiar velocity. The direction of this motion aligns partially with Shapley's location. This alignment helps verify that the gravitational pull of the Shapley region contributes to the velocity field. The combination of this data with galaxy surveys strengthens the conclusion that Shapley is one of the most influential structures in our cosmic neighborhood. The idea that distant structures affect our motion prompts further questions about how interconnected the cosmic web truly is. Galaxies do not move independently. Their motions are guided by the gravitational landscape around them. In some ways, this landscape resembles a set of long, gentle slopes and valleys created by the distribution of mass. Shapley is one of the deepest of these valleys. Galaxies respond to this curvature slowly, tracing paths that reflect the underlying gravitational potential. These long-term flows can be viewed as evidence of the interconnected nature of the universe. A galaxy's path is shaped not only by the matter within its own cluster or group, but also by distant structures it may never reach. The influence of Shapley extends into regions that will remain forever separated from it due to cosmic expansion. Yet while they remain separated, the initial motion imparted by Shapley's gravity continues, a reminder of how far-reaching gravitational effects can be across cosmic time. Another interesting aspect of Shapley's gravitational pull involves the relationship between cosmic voids and dense regions. The universe contains enormous voids where very few galaxies exist. These voids expand faster than average regions due to their low density. In contrast, regions like Shapley with high density resist this expansion more strongly. As voids grow and dense regions hold together, galaxies tend to drift from voids toward denser areas. This overall trend, sometimes described as a slow migration from emptier to heavier regions, contributes to the motion towards structures like Shapley. The contrast between voids and superclusters amplifies these flows, emphasizing the gravitational effect of dense regions. The study of Shapley's gravitational influence continues to evolve as deeper surveys and more precise measurements become available. Modern instruments can detect galaxies at greater distances and map their motions more accurately. These improvements refine the details of the velocity field and show how Shapley compares to other large structures. While some newer discoveries hint at even larger structures on different scales, Shapley remains one of the dominant influences within several 100 million light-years of our region. Its gravitational pull plays a significant role in shaping how astronomers understand the movement of the Milky Way and nearby galaxies. Without including Shapley in the models, the velocities do not match observations. Including it brings the models closer to the data. This interplay between observation and theory helps improve the accuracy of cosmological models. Shapley serves not only as an object of interest, but as a tool for refining our understanding of how gravity operates across vast distances. Most discussions about the motion of galaxies begin with the idea of expansion, because expansion sets the overall direction of movement across the universe. But once that general trend is understood, something far more subtle starts to appear in the data. Galaxies do not simply follow the expansion evenly. They drift, they lean, they deviate from the expected path in ways that reveal hidden influences scattered across enormous distances. When astronomers first began to study these deviations carefully, the clues did not point in a single direction. Instead, they pointed to several regions, each contributing its own pull. Among these, 2 regions stand out as the most significant for our corner of the cosmos. One is the Great Attractor, the other is the Shapley concentration. Together, they form a combination of gravitational influences that help shape the long-term motions of thousands of galaxies. The recognition of the Great Attractor came earlier, emerging from surveys in the late 20th century. Before then, astronomers noticed that the Milky Way, along with many nearby galaxies, was moving at a higher speed and in a particular direction that didn't align with the expected expansion rate. This indicated the presence of an unseen mass concentration. The data showed that the motion wasn't random. It pointed toward a region in the sky obscured by the Milky Way's dust, located in the direction of the constellations Norma and Triangulum Australe. At first, this region appeared mysterious. It didn't reveal itself easily in visible light due to the zone of avoidance, but gradually observations in infrared, radio and X-ray wavelengths revealed clusters of galaxies behind the dust, along with evidence of substantial mass. The Great Attractor turned out to be a broad region containing several clusters, including the Norma cluster, and large amounts of dark matter. It wasn't a single object pulling everything toward it. It was a large-scale concentration of matter situated in a part of the sky that earlier surveys struggled to penetrate. The discovery of this region helped explain a significant portion of the peculiar motion observed in local galaxies. But it didn't explain all of it. Even after accounting for the mass of the Great Attractor, the observed drift of galaxies, including the Milky Way, was larger than the gravitational influence of that region alone could justify. That gap in the explanation set the stage for the recognition of the Shapley concentration's role. When astronomers extended their surveys farther into space past the Great Attractor, they encountered the enormous mass of the Shapley region. Its location aligned in a similar general direction as the Great Attractor, but it lay much farther away. This alignment made it challenging at first to separate the influence of one from the other, but once the distances and cluster masses were measured more precisely, it became clear that Shapley contributed significantly to the acceleration of galaxies toward that region of the sky. The interplay between these two structures is what makes the study of galaxy motions in our part of the universe especially interesting. The Great Attractor provides a strong, relatively nearby pull. The Shapley concentration adds an even larger but more distant pull. Together they guide the motion of our local group and many other nearby galaxies. The velocities involved are not large in human terms. They amount to a few hundred kilometers per second, which, while extremely fast compared to everyday experience, is gentle and steady when viewed on cosmic scales. But these velocities persist, guiding galaxies slowly over millions of years. To get a sense of how astronomers separate these influences, consider the measurements involved. Each galaxy displays a redshift caused primarily by cosmic expansion. When the expansion component is removed, the remaining motion is the peculiar velocity. These peculiar velocities are then mapped across the sky. The direction and magnitude of these velocities reveal the overall flow of galaxies. When these flows are charted, patterns emerge. Galaxies tend to move along paths shaped by the distribution of mass. They do not wander randomly. They follow the contours of the gravitational landscape. This landscape resembles a set of extremely gentle slopes. The Great Attractor occupies one of these slopes, pulling galaxies locally. If it were the only influence, the flow patterns would point predominantly toward it. But the observed flows extend beyond that region. They continue farther, indicating that the slope does not flatten after the Great Attractor. Instead, it continues downward toward the deeper gravitational basin created by Shapley. That deeper basin explains why flows do not stop at the Great Attractor's location. They move through and beyond it, reflecting the combined influence of both structures. A useful illustration comes from the flow lines plotted in galaxy surveys. These lines trace the paths galaxies would follow if their motions were extended over immense timescales. The lines extend across Laniakea, converge toward the Great Attractor region, and then continue toward the Shapley concentration. This continuity suggests that the Shapley mass concentration helps define the overall motion of our region. Without its influence, the convergence pattern near the Great Attractor would not match observations. The interaction between these regions becomes clearer when comparing the strengths of their gravitational pulls. The Great Attractor is massive, but Shapley is even more massive. The distance to Shapley is much greater, which reduces its gravitational effect. Yet because Shapley's total mass is so large, it remains a significant contributor. The gravitational effect of a structure depends on both mass and distance. When mass is extremely large, distance becomes less limiting. Shapley exemplifies this. Its mass is so high that even at hundreds of millions of light years away, it adds a measurable component to galaxy motions. Cluster richness also plays a role in these dynamics. The Great Attractor includes several important clusters, but Shapley contains more massive clusters grouped more densely. Each of these clusters adds to the overall gravitational pull. Some clusters in Shapley's core demonstrate extreme velocities among their constituent galaxies, indicating deep gravitational wells. When these wells combine, the effect on surrounding space becomes substantial. Dense regions bend the surrounding gravitational potential more sharply than diffuse ones. The Shapley region's density causes its gravitational influence to stretch outward across large distances. Infrared surveys helped uncover the full shape of the Great Attractor. These surveys could see through the dust of the Milky Way, revealing clusters and galaxies hidden in visible light. As the image of this region became clearer, astronomers identified additional structures such as the Norma cluster, which was initially overlooked. These discoveries helped refine the mass estimates of the Great Attractor. However, even with these improved estimates, the gravitational pull from this region fell short of explaining the motion toward that part of the sky. This mismatch would have been more puzzling had Shapley not been discovered earlier. The Shapley concentration had been known since the mid-20th century, but not fully understood. Once redshift surveys revealed its enormous depth and richness, the missing component in the velocity field became clear. Shapley was the deeper anchor behind the Great Attractor. It did not pull everything on its own, but it formed the second stage of a combined gravitational region that extends across hundreds of millions of light years. As deeper measurements became available, the relative contributions of the Great Attractor and Shapley could be estimated more accurately. Studies suggest that the Great Attractor accounts for a significant portion of the peculiar velocity of the local group, but Shapley adds a substantial component as well. In some analyses, Shapley accounts for as much or more of the total motion as the Great Attractor does, depending on the dataset and the model used. The balance between these influences remains an active area of research, but there is broad agreement that Shapley plays a major role. The large-scale structure flowing towards Shapley provides additional evidence of its importance. Galaxies on the near side of Shapley are moving toward it. Galaxies on the far side appear to be moving toward it as well, though these motions must be interpreted through a combination of redshift and distance measurements. This convergence is a hallmark of a dense region. When multiple flows come together, it usually means the region at the center of the flows is massive. In the case of Shapley, the convergence from multiple directions highlights the extent of its gravitational influence. The presence of Shapley also helps explain the overall shape of Laniakea. The basin that defines Laniakea includes flows that extend toward the Great Attractor region, but the deeper gravitational potential beyond that region helps guide the broader structure. This interplay between near and far influences shapes the cosmic landscape around us. Without understanding Shapley's contribution, astronomers would not be able to accurately map the motion of galaxies within Laniakea. Although these motions are extremely slow by human standards, they represent a key part of how the universe evolves. Over time, galaxies move toward dense regions. Clusters grow as galaxies fall into them. Filaments channel matter into large structures. Voids expand as matter moves away from them. The Great Attractor and the Shapley concentration serve as examples of how this process plays out across enormous distances. Both regions represent areas where matter has gathered over billions of years. Both play significant roles in shaping the motions of galaxies today. Both illustrate how the cosmic web structure guides long-term evolution. In many respects, Shapley provides context for the Great Attractor. Without Shapley, the Great Attractor's influence would appear larger than it is. Without the Great Attractor, Shapley's influence on our region would appear smaller. Together they form a combined gravitational slope that helps define the movement of the Milky Way and the direction of the cosmic flow in our neighbourhood. These ideas become even clearer when we examine how matter moves inside the Shapley region itself. Clusters within Shapley continue to grow by pulling in nearby galaxies along the filaments that feed them. The motions inside the region provide clues about how the structure assembled over time. Understanding those motions helps us build a complete picture of how Shapley formed and why it remains one of the most influential structures in the nearby universe. Trying to picture the Shapley region as a single entity isn't very helpful at first, because nothing about it behaves like a singular object. Instead, its structure becomes clearer when you start thinking about how its many components fit together. The arrangement is not random. It has shape, but not a simple one. It has central areas where mass is concentrated, long extensions where galaxies thread together, and quieter regions around it where matter becomes sparse. In many ways, the Shapley concentration looks less like a cluster of isolated points and more like a vast interconnected landscape, where no part can be understood separately from the others. Studying this landscape reveals an architecture built over billions of years, shaped by gravity, dark matter, and the flow of material across immense distances. One of the most striking features of this architecture is the presence of its core clusters. These clusters sit at the densest parts of the region, where the gravitational potential is deepest. They are the most massive and dynamic areas in Shapley, containing thousands of galaxies bound together by dark matter halos that stretch far beyond what can be seen. These clusters formed early in cosmic history and continue to grow as surrounding galaxies drifted inward along filaments. Some of them rank among the largest known clusters in the nearby universe, and their internal motions reflect their extraordinary mass. Galaxies within these cores travel at high velocities, showing that the gravitational pull is strong and the amount of enclosed matter is enormous. Hot gas fills these core regions, heated to tens of millions of degrees through gravitational compression. Observations in X-ray wavelengths reveal this gas clearly. Its brightness and temperature indicate how massive these cluster centers are. In Shapley, the X-ray emissions from several of its clusters are intense, placing them among the brightest cluster cores observed in the local universe. This gas doesn't simply float between galaxies. It interacts with them, influences star formation, and responds to the gravitational pushes and pulls of the cluster environment. These interactions help define the character of the core regions. They aren't quiet places. They are dynamic environments shaped by mergers, collisions, and constant movement. Outside these cores, the architecture shifts. The clusters are connected by filaments, some of which stretch for tens of millions of light years. Filaments act as highways for matter. Galaxies, gas, and dark matter flow along them gradually, feeding the larger clusters at the ends. These flows aren't fast by human standards, but over billions of years they build substantial structures. The filaments in the Shapley region appear thicker and richer than those in many other parts of the universe. This suggests that the region collected substantial material early in its history. These filaments are not simply lines of galaxies. They contain dark matter, which forms the underlying structure, and they often contain diffuse gas that has not yet collapsed into galaxies. Mapping these filaments takes careful observation. Galaxies provide the visible markers, but the true shape of a filament depends on the distribution of dark matter. Astronomers infer this distribution by measuring how galaxies move and by studying gravitational lensing. In the Shapley region, the filaments are detected as elongated stretches of galaxies with coherent motions, indicating that they are part of the same underlying structure. Some of these filaments extend toward other clusters outside Shapley's immediate boundaries, linking it to the surrounding cosmic web. This connectivity is one of the reasons the region has grown so massive. Material from connected structures has flowed into Shapley over long periods, increasing its overall mass and deepening its gravitational basin. Between the cores and filaments lie regions where galaxy density decreases. These areas aren't empty, but they're less crowded. They give the structure room to transition between highly concentrated nodes and the long strands connecting them. Even in these transitional zones, the motion of galaxies is not random. They still respond to the gravitational pull of the core regions, drifting gradually toward the densest parts of the structure. These areas also provide valuable insight into the boundaries of Shapley. The gradual decline in density helps astronomers determine where the structure's influence begins to give way to the influence of surrounding regions. Beyond these transitional zones lie the voids, and the contrast between these voids and the core regions is striking. Voids are vast spaces where very few galaxies reside. They are some of the largest low-density regions in the universe. A void doesn't have a precise shape. It stretches between filaments and clusters like a quiet expanse. Voids matter because they shape the flow of material. matter tends to move from lower density regions to higher density regions over time. Voids expand as material flows outward. The Shapley region sits partly surrounded by several substantial voids. The presence of these voids enhances the gravitational contrast between dense and empty regions, which contributes to the overall movement of galaxies towards Shapley. Even though the voids are less populated, they play a key role in defining the architecture of the cosmic web. The boundaries between voids and filaments create the sharpest density contrasts. These contrasts help channel matter along particular paths. The Shapley concentration gained much of its mass because the surrounding voids directed material away from emptier areas and into the richer filaments. Over enormous periods, this made the region more massive than the typical supercluster. The architecture grew more pronounced as these processes continued. The combination of dense nodes, thick filaments, and expansive voids forms the structure we observe today. In many observations, the core regions of Shapley stand out, not only because they are massive, but because they are surrounded by multiple layers of structure. The clusters within Shapley's central zone did not form in isolation. They grew through repeated mergers with smaller clusters and groups. Evidence of past mergers can be seen in the disturbed shapes of some clusters, the asymmetry in X-ray emissions, and the existence of shock fronts in the hot gas. These signs indicate that Shapley's central architecture is dynamic and still evolving. The clusters continue to interact with one another, and these interactions generate motions that ripple outward across the region. Another part of the architecture involves the distribution of dark matter halos. Every cluster within the Shapley region contains a dark matter halo, and these halos overlap with one another in the core regions. This overlapping creates a deep gravitational well. The shape of this well can be inferred from how galaxies move and how the hot gas settles within it. In some parts of Shapley, the halo overlap is so strong that the combined gravitational effect resembles that of a single enormous halo, even though it is built from the contributions of many separate clusters. This combined effect gives the structure much of its gravitational power. The architecture of the Shapley region has another notable feature: its asymmetry. Unlike some superclusters that appear fairly balanced when mapped in detail, Shapley has a central core that is more densely packed on one side than the other. This asymmetry may reflect the original density fluctuations that seeded the structure, or could result from the way material has flowed into the region over time. The filaments on one side of the structure may have delivered more material, or the surrounding voids may be distributed unevenly. Studying these asymmetries helps astronomers understand how the structure grew and how its environment influenced that growth. The large-scale architecture of Shapley also includes subclusters and galaxy groups that sit just outside the densest regions. These subclusters act as transitional features. They often lie at the ends of filamentary extensions and gradually merge with the core clusters as they move inward. These groups are not as massive as the main clusters, but they contribute significantly to the overall mass budget of the region. Over billions of years, many of these groups are expected to merge with the larger clusters, adding to their halos and deepening the gravitational potential in the central areas. When visualized in 3 dimensions, the Shapley concentration resembles a series of interconnected peaks and ridges. The peaks represent the massive clusters. The ridges are the filaments connecting them. The lower areas between them form the transitional zones, and beyond those lie the voids. Each part influences the others. The peaks grow by attracting material from the ridges. The ridges form pathways that bring matter from surrounding areas. The voids expand as material leaves them. This process creates a dynamic landscape that evolves over cosmic time. Shapley's architecture is not static. It changes as clusters merge, galaxies move, and dark matter shifts in response to gravitational forces. One of the reasons Shapley stands out among superclusters is that most other known structures do not exhibit such concentrated architecture. Some are spread out more diffusely. Others lack the dense cores that make Shapley so prominent. Still others are dominated by 1 or 2 clusters rather than many. Shapley's combination of multiple massive clusters linked by thick filaments makes it one of the most robust nodes in the nearby cosmic web. Its architecture reflects both the initial conditions of the early universe and the long-term evolution of matter driven by gravity. Understanding its architecture helps astronomers refine models of structure formation. If the early universe had been too smooth, structures like Shapley wouldn't exist. If it had been too clumpy, structures more extreme than Shapley would be common. The existence of Shapley as a rare but not impossible feature helps support the idea that the universe grew from moderate initial fluctuations. Simulations of cosmic evolution attempt to reproduce structures like Shapley. When these simulations generate regions with similar architectures, it provides evidence that the models are accurate. When they fail to do so, it suggests that adjustments to the models may be necessary. The story of the Shapley region can't be told without addressing the influence of something we never see directly. Everything we observe in the structure, every galaxy, every cluster, every long filament stretching across tens of millions of light years, rests on the foundation of matter that does not emit light, does not reflect it, and does not interact with it in any familiar way. This unseen matter shapes the universe silently, deciding where galaxies form and how clusters grow. In the Shapley concentration, the presence of dark matter is so extensive that without it the entire region would look completely different. Understanding Shapley means understanding the role this invisible component plays in shaping the architecture of one of the most massive structures ever identified. It's important to begin with the recognition that dark matter is not an optional part of cosmology. It is a necessary part. The motions of galaxies, the behavior of clusters, and the distribution of large-scale structures cannot be explained by visible matter alone. When astronomers measure how fast galaxies move within clusters, the speeds are far too high to be supported by the gravity of stars and gas. The clusters should fly apart, but they don't. Something unseen provides the gravitational force required to hold everything together. That same unseen matter shapes structures even on the scale of superclusters. In the Shapley region, dark matter is the backbone, the framework on which everything else is assembled over billions of years. The density of dark matter in Shapley becomes clear through multiple lines of evidence. The first and most intuitive is the internal motion of galaxies within its clusters. The galaxies move rapidly, more rapidly than visible matter alone can account for. This requires a large amount of mass concentrated within a relatively small volume. When these velocities are measured and applied to the equations of gravitational equilibrium, the inferred mass becomes enormous, far beyond what could be produced by the stars and hot gas that we can directly observe. This difference between visible and total mass is one of the first clues that dark matter dominates the structure's internal dynamics. Hot gas provides a second line of evidence. In massive clusters, gas falls inward and becomes heated to extreme temperatures as it settles into the gravitational well. The temperature of this gas corresponds to the depth of that well. In Shapley's core clusters, the gas is shockingly hot, reaching tens of millions of degrees. Gas this hot requires an enormous gravitational field to compress it so strongly. Again, visible matter cannot generate fields that deep. Only large quantities of dark matter can explain these temperatures. When X-ray telescopes observe these clusters, the brightness and extent of the hot gas indicate the presence of enormous halos of unseen matter. A third line of evidence comes from gravitational lensing. Light passing through a massive region becomes bent by gravity, producing distortions in the shapes of background galaxies. The amount of distortion reveals the mass of the foreground structure. Even though the Shapley region is distant, portions of it demonstrate detectable lensing effects. These lensing measurements confirm that the total mass is far larger than what can be accounted for by visible matter. Combined with the other methods, the lensing results reinforce the conclusion that dark matter constitutes the majority of the mass in Shapley. These three methods, galaxy velocities, gas temperatures, and gravitational lensing, converge on the same understanding. the Shapley concentration contains an enormous amount of dark matter, far more than the visible matter it contains. This dark matter did not simply accumulate passively, it shaped the entire development of the region. From the earliest moments after the Big Bang, dark matter formed clumps and filaments due to slight variations in density. These clumps grew as more matter flowed into them, attracting both dark matter and ordinary matter. Over billions of years, the densest of these clumps became the seeds of galaxy clusters. Dark matter determined where galaxies would form, where they would cluster, and how they would move. In the Shapley region, the early density fluctuations must have been unusually large. Simulations show that structures of this size form from the upper end of the initial distribution of density variations. Only the rarest, highest peaks produce such massive superclusters. These early peaks were dominated by dark matter, which collected into deep gravitational wells. Once those wells formed, ordinary matter followed. Gas cooled and condensed into stars. Galaxies assembled and merged. Clusters grew and collided. But the underlying dark matter determined the outlines of these processes long before the first stars in the region were born. What makes Shapley fascinating is the way its dark matter halos overlap. Each cluster has its own halo, extending far beyond the visible boundaries. In the densest parts of the region, these halos overlap so strongly that the combined gravitational potential resembles a single massive structure rather than a group of individual clusters. This overlapping halo configuration explains much of the gravitational strength observed from outside the region. When an astronomer looks at the Shapley concentration from far away, the gravitational effect appears to arise from a wide and deep basin. But up close, it becomes clear that the basin is composed of many interconnected dark matter halos, each adding its own weight to the larger structure. Filaments provide another view of how dark matter shaped Shapley. These long, thin structures consist largely of dark matter. The galaxies we see along the filaments are simply the visible component of much larger dark matter strands. In Shapley, the filaments are especially thick, which suggests that the underlying dark matter density is higher than in typical regions of the cosmic web. These dark matter filaments act as pipelines that transport matter into the central clusters. Over billions of years, gas and galaxies flow along these filaments, deepening the gravitational wells and adding to the structure's mass. This flow of matter is slow but steady. Gravity pulls material toward the densest parts of the filaments. As that material moves, it begins to heat, interact, and eventually form new galaxies or merge into existing ones. The dark matter dictates the pathways of this flow. Without the dark matter scaffolding, galaxies would not arrange themselves in the filamentary patterns we observe. They would be scattered more randomly, and structures like Shapley would not form in the same way. The existence of these connections reveals just how significant dark matter is in assembling large-scale cosmic structures. Void regions reinforce the role of dark matter as well. Voids are areas where the density of matter, both visible and dark, is extremely low. These low-density regions expand faster than their surroundings. They grow larger as matter flows away from them and toward denser areas. The presence of several substantial voids surrounding the Shapley region helps shape its architecture. As the voids expand, they push material outward into the surrounding filaments. Those filaments then direct that material towards Shapley's core. Over time, this strengthens the region further. The voids and the Shapley concentration form complementary components of the cosmic landscape, each contributing to the overall development of the structure. Simulations of cosmic evolution show that structures as massive as Shapley form only in regions where dark matter was initially far above the average density. These regions act as attractors in the early universe, shaping the distribution of matter on large scales. When astronomers simulate the cosmic web using dark matter alone, without adding any visible matter, the resulting structures look remarkably similar to what we observe in real surveys. This reinforces the idea that dark matter is the driving force behind the formation of superclusters. Shapley's dark matter, Distribution provides a strong real-world example of these simulated structures. Another aspect of dark matter's influence is the way it shapes the internal dynamics of clusters within Shapley. Because the dark matter halos dominate the cluster mass, they dictate the orbital paths of galaxies within the clusters. These paths determine how often galaxies interact, how frequently they merge, and how the cluster evolves over time. In dense clusters, galaxy interactions are common. Some galaxies may lose gas due to interactions with the hot intracluster medium. Others may merge to form larger galaxies. All of these processes are governed by the gravitational environment created by dark matter. Dark matter also influences the temperature and distribution of hot gas. The gas settles into the gravitational potential wells created by dark matter. If the potential is deep, the gas becomes hotter. If the gas cools rapidly, it may flow toward the cluster center and form new stars. In Shapley's clusters, the gas remains extremely hot, suggesting that the gravitational potential is deep and stable. In some clusters, cooling flows may occur, leading to active star formation in the central regions. In others, feedback from supermassive black holes may prevent gas from cooling, maintaining high temperatures. In either case, the behavior of the gas reflects the influence of the dark matter halo. As telescopes become more powerful, astronomers can map the dark matter distribution with greater precision. For the Shapley region, these maps reveal a complex network of halos, filaments, and concentrations that align with the visible structure but extend much farther. The dark matter distribution stretches out across regions where only a faint trace of galaxies is visible. These faint areas represent the outskirts of the filaments, where dark matter dominates but visible matter has not yet accumulated in significant amounts. Understanding dark matter's role in Shapley helps astronomers address broader questions about the universe. If structures like Shapley form only in regions with unusually high initial fluctuations, the number of such regions in the universe provides insight into the early conditions that shaped cosmic evolution. The rarity of Shapley-sized structures aligns with predictions from the standard cosmological model. If far more structures of this scale existed, it would imply that the early universe contained larger density variations than currently assumed. Conversely, if structures like Shapley were too rare, it would suggest that the models underestimate the growth of large-scale structures. Shapley helps bridge these extremes by serving as an example of a rare but naturally expected structure. Light from the Shapley region has been travelling toward us for hundreds of millions of years, crossing distances so large that they stretch beyond anything we encounter in everyday life. When we observe that light now, we're not seeing Shapley as it exists today. We're seeing it as it was long before humans existed, long before Earth looked the way it does now, and long before many of the galaxies within the structure had reached their current shapes. Starlight is one of the most patient messengers in the universe. It carries information across unimaginable spans of time, preserving a record of events that unfolded long before our species opened its first observatory. The age of the light we receive from Shapley sets the stage for understanding how the region evolved. At a distance of around 650 million light-years, every photon reaching us began its journey at a time when Earth was entering a period of dramatic change. The atmosphere was filling with oxygen produced by simple organisms. Plants had not yet appeared on land. Animals were still distant possibilities. Meanwhile, galaxies in the Shapley region were undergoing interactions and mergers. Clusters were pulling themselves together, and dark matter halos were shaping the architecture that continues to grow today. When that light left its birthplace, the massive clusters in Shapley were already established but far from finished. We see them at a moment frozen in the long history of cosmic evolution. Because the light takes so long to arrive, observations of Shapley offer a window into the deep past. Astronomers use this information to reconstruct how the structure formed. By studying the brightness, colour and spectra of galaxies in the region, they can determine the ages of star populations, the amount of gas available for new star formation, and the history of mergers. These details help reveal what the region looked like at the time the light left. When compared with observations of nearby clusters, which show galaxies at more recent stages of evolution, astronomers can trace how massive structures change over time. Galaxies in the Shapley region show signs of having gone through long histories of interaction. Many appear elliptical, with smooth shapes and little gas left for forming new stars. These elliptical galaxies are common in large clusters because the dense environment strips gas from galaxies over time. When galaxies fall into massive clusters, they experience pressure from the hot intracluster medium. This pressure can remove gas, preventing new stars from forming. As a result, galaxies gradually stop producing bright young stars and become dominated by older, redder ones. This process, known as quenching, is widespread in Shapley's core regions. The light we see from those galaxies often comes from older, long-lived stars. In contrast, some of the galaxies located in the filaments and outskirts of Shapley still contain gas and younger stars. These galaxies have not yet entered the densest parts of the structure. Their starlight is bluer, indicating ongoing star formation. They represent earlier stages of evolution, showing what galaxies look like before they fall into the clusters at the core. Studying these galaxies helps astronomers understand the supply of new material entering Shapley. Over billions of years, many of these galaxies will drift inward, lose their gas, and become more like the older galaxies in the central clusters. The starlight we observe also preserves evidence of mergers and collisions between galaxies. Galaxies do not remain isolated for long in dense environments. They pass near each other, influence each other gravitationally, and sometimes merge. These mergers can trigger new star formation by compressing gas clouds. The resulting burst of star formation produces bright clusters of young stars. Eventually, these new stars age, and the galaxy settles into a quieter stage. The Shapley region contains many galaxies showing signs of past mergers, distorted shapes, extended halos, and faint streams of stars pulled out by gravitational interactions. These features are best seen in deeper images that capture the faintest light around galaxies. Another important source of information comes from the brightest galaxies in Shapley's massive clusters. These galaxies, known as brightest cluster galaxies, or BCGs, sit near the centers of their respective clusters. They are often huge, with extended envelopes of stars that stretch far into the surrounding space. BCGs form through repeated mergers with smaller galaxies that fall into the cluster. Each merger adds stars, gas, and dark matter to the central galaxy, increasing its mass. The starlight from these BCGs carries signatures of these events. Their spectra show combinations of old and intermediate age stars, along with occasional signs of past star formation cycles. The intracluster light provides another clue about Shapley's history. This is light emitted by stars that do not belong to any particular galaxy. Instead, these stars drift freely through the cluster after being stripped from galaxies during mergers or interactions. Intracluster light is faint and difficult to detect, but modern telescopes are sensitive enough to capture it. In Shapley's core regions, this diffuse light is substantial. It reflects the long record of galaxy interactions within the clusters. Every faint star in this diffuse glow represents a past event, a tidal encounter, a merger, or a slow stripping of material. Because the Shapley region is rich in clusters, it also produces strong X-ray emissions from hot gas. Although this gas does not emit visible starlight, it affects starlight by interacting with it and altering its path. The gas scatters some photons and absorbs others. These interactions help astronomers trace the distribution of the hot gas, which in turn reflects the gravitational potential shaped by dark matter. By comparing X-ray maps with optical starlight maps, astronomers can match the positions of galaxies and hot gas, linking visible matter with the underlying dark matter structure. The starlight also carries chemical signatures that tell the story of how many generations of stars have lived and died in the region. When stars go through their life cycles, they fuse lighter elements into heavier ones. These heavier elements, known collectively as metals in astronomy, enrich the gas in galaxies when stars explode as supernovae or lose outer layers. The presence of these metals in starlight reveals how long stars have been forming in the region and how active the galaxies were during different stages of Shapley's history. In the core regions, where star formation slowed long ago, the level of metal enrichment tends to be high, reflecting many generations of stars that have lived and died. In the outskirts, where galaxies are younger and still forming stars, the metallicity varies more widely. Starlight also helps determine the distances to the clusters in the region. By measuring how bright certain types of stars or galaxies appear, astronomers can estimate their distances. Standard candles such as Type-Ia supernovae provide useful distance markers. When such an event occurs in a galaxy within the Shapley region, astronomers can calculate how far away it is. These distance measurements help confirm which clusters belong to the Shapley concentration and how the structure extends into surrounding areas. Accurate distances are crucial for creating three-dimensional maps of Shapley, which reveal the depth and shape of the entire structure. One of the interesting challenges in studying starlight from Shapley is that some parts of the region lie behind the Milky Way's disk. Dust and stars in our own galaxy obscure the view, making it harder to detect background galaxies. To overcome this difficulty, astronomers use infrared observations, which can pass through dust more easily. Infrared starlight from Shapley's galaxies reveals features that are hidden in visible light. By combining infrared and optical data, astronomers gain a more complete picture of the region's galaxies, including those located near the zone of avoidance. The Shapley region also provides opportunities to study the evolution of galaxy clusters. Clusters grow as smaller groups and individual galaxies fall inward. As these objects enter the cluster environment, their starlight changes. Gas may be stripped, altering star formation rates. Interactions with other galaxies can distort their shapes. By comparing galaxies at different distances from the cluster centers, astronomers can track these evolutionary processes. The outer regions show galaxies that have not yet fully adapted to cluster life. The inner regions show galaxies that have undergone significant transformation. These comparisons reveal the gradual progression of galaxy evolution driven by the environment. Beyond the clusters, the filaments stretching through Shapley also contain important starlight clues. These regions are less dense, but they still contain galaxies that contribute to the overall picture. The light from filament galaxies shows a wider range of star formation histories. Some galaxies in the filaments are forming stars actively. Others are transitioning toward older, quieter stages. These variations help illustrate how galaxies change as they move along the filaments toward the denser regions. The filaments act as pathways not only for matter, but also for the evolution of galaxies themselves. The starlight we observe today also allows astronomers to compare Shapley with other similar structures. By examining the ages, metallicities, and star formation rates in Shapley's galaxies, researchers can determine how the region compares to other massive superclusters. Some structures may be more evolved, with older stars dominating their light. Others may be less evolved, with more active star formation. Shapley's combination of massive clusters and rich filaments places it among the more mature structures, but it is not static. New galaxies continue to fall in. Interactions continue to shape the region. The starlight reflects these ongoing processes. Even though the light from Shapley shows us the region as it existed long ago, it also hints at its future. The galaxies undergoing mergers now will likely form larger systems. The clusters that appear separate today may merge over billions of years. The starlight we observe is one frame in a long sequence of events. As Shapley evolves further, its light will continue to change. Future generations observing the region will see it differently, just as we see it differently from how it appeared hundreds of millions of years ago. All of this information, ages, temperatures, metallicities, motions, interactions, comes from analysing starlight that has crossed unimaginable distances. Understanding a structure as vast as the Shapley concentration would be impossible without reliable ways to measure distance, motion, and scale across enormous stretches of space. Nothing about this task is straightforward. Light takes hundreds of millions of years to reach us. Galaxies drift slowly, with motion so subtle that they're nearly impossible to detect without precise instruments. And the farther away something lies, the harder it becomes to separate its intrinsic brightness from the effect of distance. Yet astronomers have developed a set of tools capable of revealing the outlines of structures so large that they would dwarf entire clusters of galaxies. These tools allow us to transform faint points of light into detailed maps of the universe. One of the most basic challenges is determining how far away something is. In everyday life, distance is measured through physical motion, triangulation, or depth perception. But nothing like that works at cosmic scales. The nearest galaxy outside the Milky Way is so far away that standard methods are useless. For objects hundreds of millions of light-years distant, the difficulty grows even more daunting. Astronomers rely on a hierarchy of techniques, each suited to particular ranges. The closer methods build a foundation, and the methods that reach farther rest on those earlier measurements. Without this ladder of techniques, the distance to the Shapley region would be impossible to determine. The first step on this ladder often involves parallax, a method that measures how a star appears to shift against the background when Earth moves from one side of its orbit to the other. For nearby stars, this shift can be measured precisely, but parallax is limited. Beyond a few thousand light years, the apparent shift becomes too small to detect with standard instruments. Modern satellites like Gaia extend this range significantly, but parallax still cannot reach the distances needed to measure faraway superclusters. To explore deeper regions, astronomers turn to standard candles. These are objects whose intrinsic brightness is known or can be calibrated. If the true brightness is known, comparing it to the observed brightness reveals the distance. Among the most important standard candles are Cepheid variable stars. These stars pulse at regular intervals, and the period of the pulses correlates with their true brightness. Cepheids exist in nearby galaxies, making them useful for measuring distances beyond the reach of parallax. But they do not appear in very distant galaxies, so astronomers must rely on other indicators for greater distances. Type Ia supernovae provide one such indicator. These stellar explosions occur when a white dwarf reaches a critical mass and detonates. Because the conditions for these explosions are similar across different galaxies, they produce a consistent amount of light. When a type Ia supernova appears in a distant galaxy, astronomers can use it as a reliable marker of distance. These supernovae are bright enough to be observed across hundreds of millions of light-years, making them essential for studying the distances to superclusters such as Shapley. Another important technique involves the Tully-Fisher relation, which links the brightness of a spiral galaxy with its rotation speed. Faster rotating galaxies tend to be brighter. By measuring the rotation speed, astronomers estimate the intrinsic brightness, and from that, the distance. This method works well for spiral galaxies, but the central regions of Shapley contain many elliptical galaxies, which do not rotate in the same way. Instead, the Faber-Jackson relation is used for ellipticals, linking the brightness to the speed of stars moving within the galaxy. These techniques provide distance estimates for many galaxies across a wide range of environments. Once distances are known, redshift measurements offer another crucial layer of information. As the universe expands, the light from distant galaxies becomes stretched, shifting toward longer wavelengths. The amount of this shift, the redshift, reveals how fast the galaxy is receding due to expansion. When combined with distance measurements, redshift helps map the velocity field across the universe. For Shapley, redshift surveys reveal which galaxies belong to the structure and which lie in front of or behind it. These surveys form the backbone of three-dimensional maps that show the arrangement of clusters and filaments within Shapley. Large redshift surveys such as the 2DF Galaxy Redshift Survey and the 6DF Galaxy Survey have been instrumental in mapping the Shapley region. These surveys measure the redshifts of thousands of galaxies across wide fields of the sky. When plotted together, these redshifts reveal patterns, regions where galaxies are densely clustered and areas where they are sparse. The Shapley concentration stands out as a region with numerous galaxies all sharing similar redshifts, indicating they occupy a similar distance range. This clustering in redshift space reflects the underlying distribution of mass in the region. Redshift measurements also help determine peculiar velocities, the deviations from the expected expansion rate. By comparing a galaxy's redshift with its inferred distance, astronomers can calculate whether it is moving faster or slower than expected due to expansion alone. These peculiar velocities reveal the gravitational influence of massive structures. In the case of Shapley, many galaxies in our region exhibit peculiar velocities that point toward the concentration. These motions serve as a long-range indicator of Shapley's gravitational effect. Another technique used in mapping distant structures is gravitational lensing. When light passes near a mass concentration, it becomes bent. The amount of bending reveals the mass present along the line of sight. Although strong lensing, where background galaxies appear as arcs or multiple images, is less common at the distances of Shapley, weak lensing can still be detected. Weak lensing measures subtle distortions in the shapes of many background galaxies. These distortions reveal the statistical properties of the mass distribution. When applied across wide fields, weak lensing helps identify the locations of massive dark matter concentrations, including those in the Shapley region. X-ray observations offer another valuable tool for studying distant clusters. The gas between galaxies in massive clusters becomes heated to extremely high temperatures through gravitational compression. This gas emits X-rays, which can be detected by space telescopes. X-ray brightness and temperature provide information about the depth of the gravitational potential well. In the Shapley region, several clusters exhibit intense X-ray emissions, indicating extremely massive cores. The X-ray data complements optical and infrared observations by revealing parts of the structure that might not be obvious through starlight alone. Even radio observations contribute to the picture. Radio telescopes detect emissions from neutral hydrogen clouds, active galactic nuclei, and other sources. Mapping hydrogen helps trace the distribution of gas in the outskirts of clusters and along filaments. Radio observations also penetrate the dust of the Milky Way more easily than visible light, helping astronomers identify galaxies near the zone of avoidance, where optical surveys struggle. This is particularly important for the Shapley region, which lies partly behind the plane of the Milky Way. Radio and infrared data help fill in the gaps left by optical observations. These diverse techniques work together to build a detailed map of Shapley. Each method provides different kinds of information, and when combined they create a coherent picture of the structure. For example, redshift surveys show the spatial distribution of galaxies. X-ray observations reveal the presence of massive clusters. Lensing maps show the distribution of dark matter. Infrared and radio observations detect galaxies hidden by dust. Together, these methods reveal the complex architecture of Shapley's cores, filaments, and surrounding regions. Measuring such immense structures also requires careful statistical analysis. The universe contains large variations in galaxy density, and small sample sizes can produce misleading results. When mapping something as large as Shapley, astronomers must ensure that the observed structure is not an artifact of limited data. Large surveys help reduce these uncertainties. By observing many galaxies across a wide area, astronomers can identify genuine patterns in the data. In the case of Shapley, repeated surveys and independent datasets consistently show the same concentration of mass, confirming that the structure is real and not an observational illusion. Another challenge comes from projection effects. Galaxies that appear close together on the sky may lie far apart in actual distance. Only redshift measurements can reveal whether they belong to the same structure. By combining positions with distances, astronomers construct three-dimensional maps that show the full extent of the region. These maps reveal the deep structure of Shapley, including how its clusters and filaments are arranged in space. Without such maps, the region would appear as a crowded patch of sky rather than a massive concentration stretching across hundreds of millions of light years. The accuracy of these measurements depends on how well astronomers understand the universe's expansion rate. Hubble's law provides a basic relationship between distance and redshift, but local variations in density can cause deviations. To interpret the data correctly, astronomers must account for the influence of nearby structures, including the gravitational pull from Shapley itself. Peculiar velocity models help refine distance estimates by correcting for these effects. This iterative process, measuring redshift, estimating distance, refining the model, and re-evaluating the data leads to increasingly accurate maps of the region. As telescopes continue to improve, new methods augment the traditional ones. Instruments like the James Webb Space Telescope offer unprecedented infrared sensitivity, allowing astronomers to detect faint galaxies in distant regions with greater clarity. Large ground-based surveys provide ever more detailed maps of galaxy distributions. Advances in computational power allow simulations to generate realistic models of supercluster formation, which can be compared with observations. These developments enhance our ability to measure distant structures and understand their evolution. The process of measuring the Shapley region is not simply a technical challenge. It's a way of translating faint signals from across the universe into a coherent narrative about cosmic history. Each measurement, whether a redshift value, an X-ray brightness, or a lensing signal, contributes a small piece to the larger story. When combined, these pieces reveal a structure that has grown over billions of years into one of the most massive concentrations of matter in the nearby universe. Trying to understand Shapley's place in the universe requires shifting away from the idea of it as an isolated marvel. It does stand out, its mass, its density, its gravitational influence, but none of that exists in a vacuum. Every large structure in the cosmos plays a part in shaping its surroundings, and in turn is shaped by them. The Shapley concentration is no exception. Its significance becomes clearer when viewed not as an anomaly, but as a key component of the universe's long history of matter flowing, gathering and forming structure on scales far beyond those of individual galaxies. Shapley emerged from that process, and now it actively contributes to it, participating in the slow but persistent evolution of the cosmic web. One of the most fundamental aspects of cosmic evolution is the gradual growth of structure over time. Shortly after the Big Bang, matter was distributed almost uniformly, with tiny variations in density. These variations, though small, set the stage for everything that followed. Slightly denser regions pulled in material more rapidly. Slightly emptier regions expanded more quickly. Over billions of years, this imbalance amplified itself. Dense regions became denser, voids became emptier. Filaments formed between the densest regions, channeling material along predictable pathways. Superclusters emerged as the most massive nodes within this network. Shapley, sitting near the high end of the mass spectrum, represents one of the clearest examples of how this long evolutionary process plays out. In the language of cosmology, this process is known as hierarchical structure formation. Small structures form first: dwarf galaxies, small dark matter halos, and early gas clouds. These structures merge to form larger ones. Over time, these grow into groups, then clusters, and finally superclusters. This progression explains why large structures like Shapley contain many smaller components that share similar motion and location. They grew together, merging gradually as gravitational attraction pulled them into a common basin. Shapley's extraordinary mass suggests that the region began with one of the largest early density peaks, collecting more and more material as the universe expanded. Dark matter played the primary role in this evolution. Its distribution determined the shape of the cosmic web, and everything else followed its gravitational influence. The densest dark matter regions formed the seeds of galaxy clusters. As these regions grew, the surrounding matter flowed toward them along the filaments. In the Shapley region, this flow must have been unusually strong. The number of massive clusters in the structure implies repeated cycles of mergers and accretion. These processes shape not only the mass of the region, but also its internal structure. Each newly arrived group or cluster carried its own galaxies, gas and dark matter. Their gradual merging helped build the architecture observed in Shapley today. Shapley's place in cosmic evolution also becomes clear when examining the motion of galaxies on large scales. Galaxies do not travel randomly through space. Their paths are guided by gravitational potential wells formed by large structures. When astronomers map the velocity field across nearby regions, they find that many galaxies move toward the general direction of Shapley. This motion reflects the gravitational influence of the structure, but it also reflects the broader pattern of how matter flows in the cosmic web. Material tends to drain toward dense regions, following the lines of the filaments. This process is ongoing, even today. Shapley continues to grow as galaxies fall inward, adding to its mass and altering the distribution of matter on large scales. The influence of Shapley extends well beyond its immediate boundaries. It affects the shape of cosmic flows across a significant portion of the nearby universe. These flows form a kind of circulation system, where matter moves from low-density regions into richer ones. The Shapley concentration, being one of the densest structures in the region, acts as a major sink for these flows. The motion of the Milky Way and its neighbours reflects this effect. Even though the Shapley region lies hundreds of millions of light-years away, its gravitational pull contributes meaningfully to the motion of our galaxy. That influence helps reveal the interconnected nature of cosmic evolution. But Shapley's role doesn't end with its long-range gravitational pull. It also influences how clusters and galaxies evolve within it. Cluster environments are harsh. The hot intra-cluster gas strips material from galaxies. Interactions between galaxies alter their shapes. Mergers transform smaller systems into larger ones. Star formation slows in the core regions as gas becomes scarce. These changes reflect the broader trend of galaxy evolution in dense environments. Shapley offers an extreme version of this environment. Its clusters contain galaxies that have undergone significant transformation. Their distribution of old stars, their lack of gas, and their smooth elliptical shapes reveal a long history of interaction. These features are not unique to Shapley but occur in all massive clusters. However, because Shapley contains so many massive clusters concentrated within one region, it becomes a powerful laboratory for studying these evolutionary processes. Even the intra-cluster light observed in Shapley contributes to this understanding. This faint glow, produced by stars stripped from galaxies, reflects the number of interactions that have taken place. The amount of intra-cluster light in Shapley's core regions is significant, suggesting a long and complex history of mergers and tidal encounters. These stars carry the memory of past events, preserving the record of galaxy evolution in the region. The chemical composition of these stars indicates multiple generations of star formation. Their distribution reveals how the cluster has grown over time. On larger scales, Shapley serves as a benchmark against which cosmological models are tested. Theories of structure formation predict the number and size of superclusters that should exist in the universe. Shapley sits near the upper limit of what these theories allow. Its existence alone confirms that the early universe had density variations large enough to produce such massive structures, but not so large that even bigger ones would be common. In this way, Shapley provides a constraint on cosmological parameters such as the clustering amplitude and the amount of dark matter. If Shapley were significantly larger, or if many other comparable structures existed nearby, it would challenge the current understanding of cosmic evolution. Instead, Shapley appears as a rare but natural outcome of the models. Galaxy simulations help clarify Shapley's role further. These simulations begin with initial conditions based on measurements of the cosmic microwave background. By allowing matter to evolve through gravity, researchers can generate virtual universes, In these simulations, structures resembling Shapley occasionally appear. They are rare, but they do form. Their properties match those of Shapley in broad terms. This supports the idea that the structure formed naturally from the early conditions of the universe. Without simulations, it would be harder to determine whether a structure of Shapley's size is expected or unusual. The fact that simulations reproduce similar structures confirms that Shapley fits into the broader narrative of cosmic evolution. Another way Shapley contributes to our understanding of cosmic evolution is through its role in shaping the flow of material through the cosmic web. Filaments feeding into Shapley carry galaxies, gas, and dark matter. These flows help maintain the structure's growth. They also serve as pathways along which galaxies evolve. A galaxy moving along a filament toward a dense cluster undergoes changes that reflect its environment. Its star formation may slow as it runs low on gas. It may experience tidal interactions or collisions with other galaxies along the way. These processes illustrate how environment influences galaxy evolution. Because Shapley is so massive, the effects are amplified, providing clear examples of how environment shapes the development of galaxies. The future evolution of Shapley will reflect the same processes that shaped it so far. Galaxies will continue to fall inward along the filaments. Clusters will grow as they merge. The dark matter halo will deepen as more material accumulates. Over billions of years, parts of the structure may become gravitationally bound enough to resist cosmic expansion. Other parts may eventually drift apart as dark energy accelerates the expansion of the universe. Even though Shapley is enormous, it does not escape the influence of cosmic acceleration. Superclusters lie near the boundary between gravitational binding and expansion-driven separation. Shapley's core may remain bound for a long time, but the outer regions will gradually disperse. Shapley's role in cosmic evolution is not confined to its own growth. It also teaches us how typical or atypical such structures are. By comparing Shapley to other massive superclusters, astronomers can determine whether the universe contains many similar structures or only a few. Surveys suggest that structures as massive as Shapley are rare. This rarity supports the idea that the early density fluctuations needed to produce such structures were uncommon. The presence of one Shapley-like structure nearby does not imply that many more lie hidden elsewhere. Instead, it suggests that Shapley represents one of the exceptional cases that formed naturally but infrequently. Another important aspect involves the effect of Shapley on the surrounding velocity field. By contributing to the motion of galaxies in our region, Shapley plays a part in organizing the large-scale flows that shape the distribution of galaxies. These flows form part of the overall structure of the cosmic web. Without Shapley's contribution, the flow patterns would look different. The presence of such a massive structure influences how clusters and groups move. This effect is not only a result of the structure's mass, but also a reflection of how matter responds to the large-scale gravitational landscape. All of these contributions, taken together, show that Shapley is both a product and a driver of cosmic evolution. It formed from the earliest density variations, grew through the flow of matter along filaments, and now shapes the motion and development of galaxies on large scales. Its significance extends far beyond its own boundaries. It connects the early universe to the present-day cosmic web, serving as a reminder of the continuous process through which structure emerges, grows, and influences its surroundings. It's difficult to think about the Shapley concentration without eventually drifting toward the larger question of what all this mass and structure implies for the future of the universe itself. A region as enormous and influential as Shapley does more than bend the paths of galaxies. It provides a rare glimpse into how cosmic evolution unfolds on its grandest scales, revealing not just how matter has behaved for billions of years, but how it will continue to behave as the universe marches forward. Every cluster within Shapley, every filament feeding into it, every unseen dark matter halo shaping its boundaries, each part offers a clue about the future, because understanding a structure so massive means understanding the forces that govern the expansion and ultimate fate of everything. To begin thinking about the future, it helps to acknowledge that the universe today looks nothing like it did a few billion years after the Big Bang. In those earlier times, matter was more densely packed, structures were still forming rapidly, and gravity had more leverage over the shape of the cosmos. Over time, however, expansion has become increasingly dominant. The discovery of dark energy was the turning point in our understanding. Once astronomers recognized that the universe is not just expanding but accelerating in that expansion, everything about the long-term forecast shifted. Structures still form, but the expansion gradually isolates them, making it harder for matter to gather into even larger concentrations. Despite this acceleration, Shapley exists, and its existence speaks volumes about how strong gravitational influence can be when enough mass gathers in one place. The region formed from one of the rare initial density peaks in the early universe, and because of that early advantage it accumulated matter more effectively than most other regions. This process continued even as expansion increased. The fact that Shapley reached its extraordinary mass, tens of thousands of Milky Way equivalents, shows that gravity remained powerful enough for long enough to build structures of remarkable size. That alone offers insight into the early balance between gravity and expansion. But Shapley also hints at the boundaries of what can form in an accelerating universe. Simulations show that once dark energy begins to dominate, it becomes increasingly difficult for matter to collapse into larger gravitationally bound systems. Structures that are already dense continue to grow to some extent, fed by the filaments that formed earlier. But entirely new large structures do not form. The cosmic web becomes locked in place. Growth slows dramatically. In this sense, Shapley represents one of the last great examples of hierarchical structure formation operating at full strength. Everything that forms after this era will be smaller or more isolated. The Shapley region illustrates another key idea about the universe's fate: the separation of gravitationally bound systems from those no longer capable of resisting expansion. On small scales, solar systems, galaxies, and galaxy clusters, gravity remains dominant. These systems hold together regardless of how fast the universe expands overall. On the scale of superclusters, however, the situation becomes more complicated. Superclusters are not entirely bound. They contain parts that will stay together and parts that will drift apart. Shapley occupies a position right at that threshold. Its central clusters may remain gravitationally connected far into the future, merging slowly as matter continues to fall inward. Meanwhile, the outskirts will gradually lose contact with the core as expansion pulls them away faster than gravity can reel them in. This partitioning of the universe into permanently bound islands and ever-widening distances reflects the long-term influence of dark energy. Over extremely long periods, galaxies outside our gravitational island will drift beyond any possible observational range, carried away by accelerating expansion. The universe will appear emptier with time as distant structures fade into darkness. Shapley offers a preview of what becomes of the larger structures in this scenario. Its core will endure, slowly evolving as clusters merge, gas settles, and stars move through their long life cycles. But its ability to influence the broader universe will fade, not because its gravity weakens, but because the expansion of space overwhelms its reach. Another clue that Shapley offers involves the relationship between voids and dense regions. We know that cosmic evolution follows a pattern in which voids expand faster than the regions around them, funneling matter into filaments and clusters. In the far future, these voids will dominate the large-scale appearance of the universe. Their expansion will stretch the filaments thin. The dense nodes will become increasingly isolated. The Shapley concentration gives us a snapshot of one of these nodes before cosmic isolation reaches its later stages. In a sense, looking at Shapley today is like looking at a structure shortly before the universe pulls the surrounding landscape away from it. The light coming from Shapley also reflects the late stages of star formation in dense environments. Most of its core galaxies have already exhausted their supply of gas. Star formation in these areas is slow or non-existent. The stars we see today in Shapley's clusters include many old, long-lived ones, along with remnants of past generations. This pattern illustrates a broader trend in cosmic evolution. Star formation across the universe peaked several billion years ago and has been declining ever since. As gas becomes scarcer and galaxies lose material through mergers, heating, and interactions, new star formation slows. The Shapley region, with its quiescent core galaxies, demonstrates the direction in which cosmic star formation is heading. Over trillions of years, newly formed stars will become rare. The universe will gradually shift toward a landscape dominated by old stars, remnants, and long-lived systems powered by slow-burning red dwarfs. Shapley also highlights the fate of large clusters. Clusters are among the most enduring structures in the universe. They remain gravitationally bound even when expansion becomes extremely strong. Their internal dynamics cause galaxies to drift toward the center, merge, and interact. Over immense spans of time, clusters settle into deeper gravitational wells, becoming smoother and more centrally concentrated. The Shapley region, with its many rich clusters, offers an example of a place where these long-term processes will be especially active. If we look ahead trillions of years, many of Shapley's clusters will have merged into single, enormous systems. These mega-galaxies will hold the remnants of thousands of galaxies that once orbited independently. Dark matter will continue to shape these systems, even as star formation slows. The dark matter halos that form the backbone of Shapley's architecture will not disappear. They will continue to hold the clusters together, but their influence will be confined to the gravitational islands they define. As expansion accelerates, these halos will no longer interact meaningfully with halos in other regions. Shapley's environment will become a closed system, separated from the rest of the universe by distances expanding faster than light can cross. The gravitational tug Shapley exerts today tells us something else about the future. Right now, galaxies across hundreds of millions of light-years move partly in its direction. But this motion will not continue indefinitely. The expansion of space will eventually outpace Shapley's gravitational pull for all but the closest galaxies. At some point in the distant future, the large-scale cosmic flow towards Shapley will end. The gravitational role that the structure plays in shaping the motion of our region will fade as the expansion isolates everything. Shapley's importance in terms of cosmic influence will become local rather than large-scale. There is also the broader implication that structures like Shapley represent the last era in which large-scale growth occurs. Once dark energy dominates fully, the assembly of megastructures becomes impossible. The cosmic web stops evolving in the way it once did. The patterns solidify, distances widen. The future becomes characterized more by separation than by assembly. Shapley sits near the transition point between these two eras. It marks the end of the time when superclusters could still grow meaningfully and the beginning of the time when the universe moves toward isolation. Another lesson comes from comparing Shapley with other structures. The fact that Shapley is near the upper limit of what cosmology predicts tells us that the universe produced only a small number of such giants. The rarity of structures like Shapley fits neatly into our models of cosmic evolution. It means the universe was neither too smooth nor too clumpy in its early stages. If the early density variations had been larger, structures even bigger than Shapley would be common. If they had been smaller, Shapley would not exist at all. The presence of Shapley confirms that the initial fluctuations had just the right characteristics to produce a universe like the one we observe. In the long-term future, the Shapley region will provide a stable anchor for whatever civilizations or observers, if any, might exist within the gravitational island defined by its clusters. Outside that island, everything will recede beyond reach. The night sky will grow emptier. The cosmic web will no longer be visible. Only the structures bound by gravity will remain accessible. Shapley's mass ensures that its gravitational island will be large and enduring, the stars within it will continue to shine for trillions of years before gradually fading as fuel runs out. Thinking about what Shapley tells us about the universe's fate also highlights how brief our observational window is. We live in a moment when the cosmic web is still visible. The light from Shapley still reaches us. The expansion has not yet accelerated to the point that distant clusters vanish from sight. We can still map superclusters, measure their influence, and trace the flows of galaxies across hundreds of millions of light years. This period, cosmologically speaking, is temporary. In the far future, structures like Shapley will slip over the horizon of observability for anyone outside their gravitational islands. Even though the long-term future may appear quiet and isolated, the present-day study of Shapley offers a unique chance to understand the universe before that isolation sets in. By observing the structure's mass, motion, and evolution, astronomers gain insight into both the past and the future. Shapley stands as a reminder of how the universe grew from small fluctuations and how it will eventually settle into a long period of separation and slow internal evolution. It's easy to lose yourself in the scale of something like the Shapley concentration. After spending so much time exploring its clusters, its filaments, its gravitational influence, and the ancient light arriving from its galaxies, the mind instinctively stretches outward, trying to accommodate distances and masses that sit far beyond anything familiar. But eventually the view shifts. Attention drifts back toward the local, toward the place where each of us listens from. The return is not abrupt. It's more like letting a distant landscape fade gradually behind you as your focus settles once again on the surroundings that feel close, quiet, and known. After tracing a path across hundreds of millions of light years and stepping through billions of years of cosmic history, there's something grounding about remembering where those observations are made from. A single galaxy in a small group on a tiny planet that orbits an ordinary star. Our home in the universe is modest by any cosmic comparison. The Milky Way is a large spiral galaxy, but not an unusual one. It sits within the local group, which contains only a few major galaxies and many small ones. That local group is part of a larger structure called the Virgo cluster, and together with neighbouring clusters it forms the Virgo Supercluster. Even that, it turns out, is just a piece of a broader structure called Laniakea. When placed against the backdrop of the Shapley concentration, our entire region becomes just one thread among many in the vast tapestry of the cosmic web. The contrast between our small corner and something as massive as Shapley provides perspective that is both humbling and strangely comforting. The journey back begins with the recognition that even though we are tiny compared to structures like Shapley, we are connected to them through gravity, motion, and the same laws of physics that shape everything in the cosmos. The fact that our galaxy drifts along flows influenced by Shapley's mass shows that we are part of a larger story. Even if the distances are too large to ever cross, and even if expansion will eventually separate regions beyond visibility, the connection exists right now. The measurements astronomers make, the light they collect, and the maps they construct all reveal a world where our home is woven into the fabric of structures extending far beyond anything we could experience directly. Returning attention to our part of the universe doesn't diminish the structure we've just explored. Instead, it places things in a context that feels meaningful. The cosmic web is full of massive superclusters, large voids, and countless galaxies. But in the midst of all that, life emerged here, on a small rocky planet orbiting a star in the outer part of an average spiral galaxy. When the light from Shapley began its journey toward Earth, our planet was inhabited only by simple organisms drifting through ancient seas. That light crossed the universe slowly and steadily, until it reached a world filled with beings capable of building instruments to detect it, analyze it, and interpret the story it carries. The quiet return to our corner of space is also a reminder of how rare and delicate our vantage point is. Everything we know about the broader universe, every measurement, every map, every discovery, comes from observing tiny variations in light arriving from distant galaxies. A small shift in wavelength reveals motion. A slight change in brightness reveals distance. Faint X-rays reveal hot gas in clusters. These subtle signals streaming from objects we will never visit inform our understanding of structures like Shapley, and all of it happens from a single point in a vast universe. The Milky Way itself, though ordinary by cosmic standards, contains its own intricate beauty and complexity. Hundreds of billions of stars orbit within it, each with its own story. Some are older than the Sun, some are younger, some host planetary systems with possibilities we haven't yet discovered. Our galaxy is shaped by dark matter halos, star-forming regions, ancient clusters, and spiral arms that sweep gracefully through space. This local environment is where our understanding begins. All of the large-scale perspectives we explore, superclusters, cosmic filaments, massive gravitational flows, emerge from the foundation built by studying our home galaxy. The local group too reflects the same processes seen in colossal structures like Shapley, just on a smaller scale. The Milky Way and the Andromeda Galaxy are moving toward each other. In several billion years, they will merge. This slow dance echoes the mergers of far larger clusters in Shapley, following the same gravitational principles. The scale is different, but the physics is the same. As we drift back toward thinking about our own cosmic neighbourhood, these parallels highlight how the processes shaping the universe repeat themselves across many scales. Even the concept of a cosmic flow, which defines much of Shapley's influence, manifests locally. The galaxies in our region flow toward the Virgo cluster, and from there toward the basin at the centre of Laniakea. These motions are gentle and unnoticeable in everyday experience, yet they reflect the same gravitational patterns seen in the motions toward Shapley. Observing our local flow reminds us that our home is part of the same grand network, shaped by the same long-range influences. The return also brings attention back to the human perspective. From Earth, the night sky looks peaceful and unchanging. Stars follow predictable paths. The Milky Way forms a soft, luminous band across the sky. None of this hints at the immense motions or massive structures influencing our galaxy's journey. Yet these structures, though hidden from direct view, are present in every shift of starlight that reaches our instruments. They shape our understanding of the cosmos even as they remain invisible in the sky, reflecting on the immense journey outward and the gentle drift back inward. Also reveals something about the nature of curiosity. Humans have always stretched outward in imagination, wondering what lies beyond the visible horizon. Ancient astronomers charted the motions of stars and planets long before the existence of galaxies was known. Today we chart the motions of entire galaxy clusters and superclusters. Each generation extends the horizon a little farther. The study of Shapley is one piece of that long tradition, a step in the ongoing effort to understand our place in the universe. This shift back toward our corner of space does not imply withdrawal from the vastness beyond. Instead, it suggests balance. The universe contains structures so large that they dwarf anything we can grasp intuitively. Yet the experience of observing them happens here in a very specific place. Our galaxy's orbit, our solar system's motion, Earth's rotation, all of these factors frame the way we perceive the cosmos. We look outward from our own position, and doing so the cosmos becomes something we can explore one step at a time, even when the scales are immense. The concept of home becomes meaningful again when placed against this vast backdrop. Earth is small, fragile, and unique, but it is also the only place from which we have ever observed the Shapley concentration. Every photon we use to understand that distant structure enters our atmosphere, passes through telescopes or instruments, and is interpreted by minds trying to comprehend its meaning. This simple connection between a distant supercluster and the tiny point where its light is received creates an unexpected sense of continuity. The cosmos may be enormous, but the act of observing it brings everything into a shared frame of understanding. Our return to the local also invites reflection on how much remains to be discovered. Shapley is not the only massive structure in the universe. Observations continue to reveal others, some even larger when measured in different ways. As instruments improve, new details emerge. Deeper redshift surveys uncover hidden clusters. X-ray telescopes detect fainter hot gas. Radio arrays penetrate dusty regions. Each new discovery expands the map. Our little corner remains a stable base of operations for exploring these wider regions. The gentle drift back toward home also highlights how much the act of perspective shapes our interpretation of the universe. When thinking about Shapley, the cosmos feels immense and almost impersonal, but when attention shifts back to the local, the universe becomes something that can be experienced from one's own vantage point, small enough to feel intimate, yet connected enough to feel vast. This duality is part of what makes astronomy so powerful. It reveals the enormous while grounding us in the familiar. As the arc of the exploration curves back toward our vantage point, the quiet continuity between the far and the near becomes clearer. The forces shaping Shapley also shape us. The light arriving from its distant clusters illuminates our instruments just as sunlight illuminates our world. The motions within Shapley reflect the same gravitational patterns that guide our own galaxy. Even the long-term fate of Shapley echoes patterns that will play out in our local region. The universe may seem overwhelmingly large, but its structures and principles apply everywhere, including here. And so, the return to our tiny corner of space is less about stepping away from Shapley and more about remembering that all of it, every cluster, every filament, every drifting galaxy, belongs to the same universe we inhabit. The story of Shapley is part of the story of everything. From our quiet spot in the Milky Way, we can observe it, measure it, and trace its evolution. The view may be small, but the reach of our understanding stretches far outward.